I'm on a quest to explore all the technologies from the Stone Age up to the age of industrialization and the steam engine. In the previous 2 marathon edits, we covered the first major historic milestones, first covering the technologies going from the Stone Age and into the mastery of the first metals and alloys of the Bronze Age. Then advancing and unlocking the technologies of iron and steel. In this next section, we're going to start progressing towards the first steps of the industrial age, while still many centuries before the steam engine. Before we can put such an engine to work, we need to explore and better understand early methods of capturing energy and putting it to work for us. So with that, we begin exploring the first forms of capturing energy, with water wheels, windmills, and wheels for harnessing human and animal power. Then we're also going to have to explore putting it to work to help mass produce crucial building materials like milled wood, while also constructing machines that will become more and more important as we get closer to the steam engine and more advanced, finely tuned machines, the lathe. In my ongoing endeavor to recreate all of humanity's technology, starting from the Stone Age, I find myself dabbling in countless crafts and never fully mastering anything. One such skill set that these projects become reliant on more and more is woodworking, something I have a decent surface level understanding of, but definitely have a lot more I could learn and master. To do that, fortunately, there are resources like the Woodworkers Guild of America, who have sponsored today's video. Whenever I take on a challenging woodworking project, I always try to turn to resources that make learning not just effective, but enjoyable. Woodworkers Guild of America is your ultimate online resource for woodworking tutorials, ideas, and techniques. Whether you're a beginner or experienced craftsman, they've got something for everyone. I've personally learned so much, from advanced joinery techniques to sharpening hand tools. One of my favorite videos recently was building shop jigs. They've really transformed how I work efficiently. Their premium videos are taught by seasoned experts who walk you through every step with clear, detailed demonstrations. Plus, their community is amazing. You can connect with fellow woodworkers to share ideas and ask questions. If woodworking inspires you as much as it inspires me, check this out. The first 1,000 of you to click the link in the description will get a full year of premium membership for just $1.49. That's access to hundreds of expert tutorials, live Q&As, and downloadable project plans for less than the cost of a coffee. So join Woodworkers Guild of America today and take your woodworking skills to the next level. Offer valid for new members only. In my ever-going quest to build myself up from the Stone Age and into my own industrial revolution, there's one machine that is potentially the most crucial. The so-called mother of machine tools, the lathe. As I begin moving into the industrial age, harnessing power from nature and using it for my own industrial needs is going to involve a lot of spinning objects, from water wheels, windmills, steam engines, and the tools that will be powered by them. For them, you're going to need a variety of circular symmetric pieces, from pulleys, gears, screws, axles, wheels, bearings, and countless other pieces. Any imperfections in their symmetry and it's gonna throw things off, possibly create a wobble, and potentially destroy the machine or at least make it less effective. Here enters the importance of the lathe. Overall, the concept is pretty simple and has very ancient origins to at least as long as the 13th or 14th century BC. Basically, a working piece of material is pinned to a single axis and is then spun by some device. Modern lathes use a motor to spin, but earlier ones used an attached cord that spins a piece of wood. Early versions were often powered with a bow, and I actually made a version of this early on in my abacus episode. However, while technically effective, it was incredibly difficult to use and very limited in what could actually be made on it. A later version of the lathe was the spring pole, which stored energy on each pole, allowing much longer rotations with less effort. During my trip out to Utah a few weeks ago, I decided to get some help in building this machine. So here with Joseph from Good and Basic and Nate from the internet, and today we built a pole lathe.
You've sawn through a piece of wood with a homemade saw.
That is awesome. Look how smooth that is. You made that.
Yeah.
That's hardcore.
That's honestly a pretty good finish. I like that.
That's not bad at all.
Neat. Oh gosh. Huh. Is that a breaking sound?
Yep. hasn't moved.
It's holding it right in that one spot.
That's awesome. Pretty close.
Yeah.
All right, you spin it. Other way. Just go for once, guys. We're gonna have this round dowel.
Need some tools to actually use on the lathe, so back home in Minnesota, I tasked Adri with the task of forging some lathe chisels to use on the new pole lathe.
We're going to forge some lathe tools for our pole lathe. We're going to make 3 chisels. This thinner stock here is going to end up being our skew chisel and our parting tool. And this thicker stock here is going to end up being our roughing gouge. Forge is hot behind me. We should probably get this heating up and get at it. Now we have our skew and our bevel formed in. So next up we're going to come back here and we're actually going to shoulder this out and start drawing out the tang where it'll attach to the handle. Now that we have our other tools done, we're going to move to some wider stock here. We're going to forge our roughing gouge. We're going to take this and we're going to shoulder it down and we're going to taper this out to form our tang before we come over and cut off the other side, chamfer it, and roll it around to form that half round shape. Let's get it hot and we should have some lathe tools.
Back in Utah, we're ready to test out the lathe. And just need to find a good springy branch to connect it to.
Okay, that should work.
What about this one?
What?
This one?
The one that we were trying to spin?
Yeah. I think maybe we should wrap it around that one.
Nah, I think we'll work without it.
Decent chance we'll still wear our way through this string after.
We just need a proof of concept. We're pretty happy about that. We waved. We waved. Adjust where the string is by moving the stick. Right. That way when you need to part this section, you can move it over here and not cut your rope.
Curious.
So dry?
Big strokes up and down. Yeah, hit yourself in the head with that branch. That's the key. That's how you know you're doing it right.
This is also why apprentices exist.
I was saying, if I were doing this, I would get used to the timing and I would have a guy whose your job is to step on things. Yeah, right. We made this bigger piece of wood into an aesthetically pleasing smaller piece of wood.
I know I look a little dumb, but the coordination is harder than it looks.
Yeah, no, it takes getting all your parts moving at once.
I mean, part of it is the awkward angle of the pedal, right?
Yes, definitely.
It's only this shaky because I'm doing it left-handed. Promise I can do it better right-handed, and no, don't ask me to try. The basic idea is we have two sharp points that stab into the end of a piece of wood so that it can rotate on those 2 points. And then we have this string here, which is attached to a long springy pole. And then we press down here and that pulls on the string. And suddenly we have a super primitive lathe that we can use to carve cylindrical stuff. Anything like chair legs or tool handles or furniture pieces or pulleys or all kinds of other useful things can be made on this. You press down with your foot and you have to work in this really funny rhythm where you're pressing the tool in only on the downstroke, you're balancing on one foot. It's very much like pat your head, rub your tummy at the same time, except like in multiple dimensions while making stuff. And it ends up being really, really fun. You agree?
It's pretty satisfying. Like, I've used powered lathes, and obviously you're gonna get a lot more done with them, but there's something really like back to the roots of the creative process with this.
I can't wipe this grin off. This is fun. We've carved out a little handle blank here. We're going to use a skew chisel and we're going to try to separate that out. There we go. My angle was wrong.
Well, good timing.
I think we're done for today.
It's a heck of a proof of concept.
Isn't that awesome?
It sure is.
Stick that on a chisel somewhere. We made a thing. We made a thing that made a thing.
Yeah, we made a thing maker.
I find something very, very, very pleasing about things that make other things.
Ended up leaving the support structure with Joseph so he could build his own version, and I brought the poppets back with me. So now I just need to rebuild that same support structure back home, have it ready to start turning any future projects, and start industrializing. Soft green wood practice on. It's gonna take a bit of practice to get the full hang of it, but I'm already able to produce some pretty nice shapes that have perfect circular symmetry. So this lathe is pretty much limited to only being able to turn wood, but it'll serve as a base as I eventually upgrade it to be powered by external sources like a water wheel, which should hopefully open things up to turning harder metals as well. Something that will prove absolutely crucial as we progress further into the industrial age. Thank you again to Joseph from Good and Basic and Nate from the internet for their help with putting this all together. Be sure to check out their channels. Nate posted his side of the collaboration we did on trying to make cast iron, so be sure to check out that if you haven't. And if you want to see more examples of wood turning with a primitive pole lathe, Good and Basic has a great video showcasing that. Thank you again to all of our supporters on Patreon. Thanks for watching. At its core, this series is about tools, how each new tool we build acts as a power multiplier, which inevitably speeds up the progress of everything. But knowing its end goal, it's hard not to want to jump to the power tools right away. Next up, I'm hoping we can start laying down the first steps towards that goal with power. After achieving the breakthrough of the material iron and formally entering the Iron Age, one of the next major developments in human history, the harnessing of nature, to provide us with free power. And ultimately, that was the far-off goal that started the Reset series, the eventual goal of doing our own industrial revolution by building a steam engine.
Love to see a steam engine that you've built from scratch.
So we start the beginning steps of that today with the first part of building a water-powered sawmill. First emerging around the 3rd century BC, water mills were one of the first ways to replace human labor with natural forces. Some of the earliest were used for the tedious task of grinding grains, was also quickly utilized for other tasks like powering bellows or trip hammers. The main water mill we'll be taking inspiration from is the Roman water-powered stone mill in Hierapolis in what is today Turkey. A pretty advanced design, it allows the cutting of stone with natural water power by utilizing gears and a crank. Instead of stone though, I want the primary focus to be milling wood and open up the possibility of building some bigger structures. So far, we've explored some of the main ways of forming squared pieces of wood, by either splitting and shaping them with wedges and draw knife, or by hewing with an axe. Both are pretty slow and labor intensive, but were only replaced when sawmills came into prominence. So we have the rough plan for the mill now. So in this first video, we're going to focus on just the saw. The rest of the mill will require lots of milled wood itself, so it makes sense to start with a tool that can help us make the rest. The saw has existed since the Bronze Age, and even forms of it were made in the Stone Age as well. However, none of them were the most effective. The teeth weren't the sharpest, they never held an edge very well, and were incredibly slow and inefficient to use. Now in the Iron Age, with a tougher metal, we can refine the technology more and hopefully make a much more efficient saw. First up, we need some tools, specifically a triangular file for grinding and sharpening the teeth of the saw. So starting with a stock rod, I used a bent piece of iron to roughly forge a triangular shape into it. Then rounded and thinned down the handle. Next, shaped a billet into a die for carving the teeth into the file. I'm roughly following the process ClickSpring explored in one of their videos previously, where they also ran into the need of making primitive files, so I recommend checking out that video for more details on this process. After forging them roughly to shape, next ground and cleaned them up and coated them in a layer of charcoal and wrapped them in clay. Then, once the clay dried, baked it in a kiln. If done correctly, this should cause case hardening, where the carbon from the charcoal alloys with the iron to form a harder steel. This will allow the file to stand up against the other iron we'll be filing. Lastly, I began adding the teeth to the file. Testing out my crude file, it cuts and grinds pretty effectively, but with a lot of labor. So to maintain my own sanity, I'm going to swap it out for a more durable modern file for the majority of the grinding. First up, we're going to try and make the actual blade for the saw. Adri here to help me, kind of guide me. A kind of expert blacksmith who previously helped us make a sword out of iron. I'm gonna get a little bit of help to kind of guide me on this. I'm gonna take this stock piece of metal, hammer it into shape, and then we're gonna use some files to put actual teeth into it. And then I'll eventually be putting this into a frame to make a frame saw that would have been used in the early Iron Age. Start hitting.
that it wants to bend over, which is not a good thing. So we just have to make sure it stays straight. And take really straight strikes. We're just going to draw it out a little bit and it goes straight up, and then we put a hole in the end. That hole is where that pin goes, and that's what holds it against the frame.
All right, so we got it all forged out. We got a hole at the one end to hold the pin and keep it there, and then a loop there to put the wedge to hold it tight. Now what you need to do now is file in the teeth.
Forming teeth is a little bit of a gray area when it comes to saws of this period. We know that generally early iron and steel saws had their teeth cut via fly press. A method that survived in modern saw making is retoothing a saw with files. It's super simple, especially for a rip saw like this, to take these blanks and file the teeth in one by one as you go down, rather than using a large fly press. Push down and cut the teeth out.
All right, so after a lot of filing and then more filing, I have all of the teeth in here, roughed in. So next I'm going to set them, which is kind of the alternating alignment. It allows you to cut a wider spot than the actual width of the blade. It allows the blade to pass through a little bit easier. It's kind of an issue I had with a lot of the other bronze attempts at saws. The teeth were a lot smaller than the actual body, so it always get jammed up. So this should hopefully allow it to clear a little bit better and get some nice wide cuts.
It's working.
Yeah. And then do it the other side, going the other way. Bend. That is actually pretty effective. It's not even sharpened yet. Yeah, that is definitely a saw. It cuts surprisingly well. Very promising, a lot better than our other saws. So next we need to put it into a frame. It's ended up being a bit more rigid than I expected. I can actually saw with it just as it is. It doesn't bend too much. But when we start going at some really large logs, putting a lot of force into it, the more tension we can have to keep it rigid, the better it'll be. So there's basically two types of frames you can do, and that's depending on if you're going to do a cross cut or a rip cut. If you do cross cut, then it's more of a bow saw where you have a frame going up. Then if you're doing a rip, you have a square frame that goes all the way around it, and that allows you to cut this way. That's what we specifically had in mind for cutting up and milling our own logs. So we have a loop here to hold a wedge, and that'll keep it tight. We have a hole for a pin. So basically we just need to make a wooden frame, put some slots in it for the blade, put in the pin and the wedge, tighten it up, and we should be good to cut. Sharpen a little bit of a point on both of these sticks and cut some grooves into the receiving ends, and then cut some notches for the blade. Should be good to assemble this guy up, and hopefully it should all fit up. Some tension. So I have the saw all completed now with a crude frame that should allow us to rip some logs, and that'll be really useful. It's going to require a lot of lumber for the sawmill. It's going to be a lot of hand power going into making the first few batches, and hopefully we can get to the point where we don't need it. Hewing and splitting logs like we have done before was also continued for a while, but this method continued to improve and get better and better, eventually to the sawmill, which is our eventual goal. Got a wedge holding the tension. That should hopefully improve effectiveness of it. So this is the kind of the very first step of the watermill sawmill, which is going to be a lot of work and a lot of bigger pieces. This is probably about the smallest piece, but even then, this one took a lot of manual labor to produce. Just having to file each tooth in, realigning it, and sharpening it, and putting it in the frame. It was about 25 hours of labor altogether, probably about $200 worth of labor using the usual minimum wage $200 saw. And we'll see how much that adds up as we get into the full sawmill. This will kind of be a running total as we slowly build our water-powered sawmill. But for now, it's human-powered. We got a lot of wood to mill, so we can start using this to cut some more square lumber and can probably produce a better frame eventually using the tool itself, and hopefully unlock some a little bit more refined woodworking as we go. We can start taking this out into the field and producing some nice square lumber. Thank you everyone for watching. Thank you to all of our sponsors on Patreon. This is just the first step of a growing larger project as we get to the industrial age. If you want to see us tackle these large projects like that, support us on Patreon. Check it out in the link below, and thanks for watching.
Should I put a quarter in?
Wood has gotten quite expensive lately, which always seems kind of weird to me because I'm pretty sure this stuff grows on trees. But to get a finished piece of wood like your standard 2x4 from a tree takes a lot of steps. And when there's a disruption to that complex distribution system, costs can suddenly skyrocket when supply can no longer meet demand. But what if you cut out the middleman and went straight from tree to milled lumber, doing every step yourself using your own hand tools? Well, let's give that a shot and see how much it would cost to produce our own simple 2x4 by doing every step ourselves. The process of going from a tree to pre-cut dimensional lumber can be a bit of a procedure that we're very detached from today. For many, a finished 2x4 feels almost completely foreign from the tree it originally came from, and is just this default modern building block for use for anything from building houses to furniture. But nevertheless, at its origin, a modern 2x4 starts its life as a tree. Usually a softwood tree, such as a spruce, pine, or fir. In the US, most of the softwood lumber comes from the West Coast, and are often harvested from second growth forests which were planted 50 to 60 years ago. Once an area is ready to be harvested, the desired trees are marked and then cut down and delimbed. From there they are transported to the sawmill. First they are ran through a debarker to remove the outer bark, then begins the milling process of slicing the logs to the desired sizes. Previously we got to film a mobile sawmill to help cut some hardwood, which shows the general method of cutting a log into dimensional lumber. The next step is the drying or seasoning of the wood, which removes all the moisture in the freshly cut wood. In the drying process, the wood will shrink from what it was cut to. Lastly, after drying, the wood is passed through planers, which gives the lumber a smooth finish with round corners. It's these last two steps that cause the 2x4 to not actually be 2 inches by 4 inches as a finished product. The shrinkage during drying and the extra milling removes about a half an inch from each dimension, leaving the modern 2x4 as actually 1.5 inches by 3.5. From here, the lumber is graded by quality and shipped out to your local lumberyard. For my 2x4, I tried to find a more local source of a tree in the Minnesota area, And after a lot of emails and exchanges with several forestry organizations and companies, I ultimately ran into a dead end on finding a good source. I ideally wanted to gain access to a tree and a forest and figure out how much a single tree would cost to buy the rights to. But a variety of issues caused that to be pretty much impossible to figure out. So after a fair amount of searching over this past summer, I found that the answer to my problems is to look within my own yard. So when I first bought this property 2 years ago, this tree was not looking the greatest, but was still alive, and I was hoping it might come back. I noticed at the end of this year that it has pretty much completely died. There are no leaves on here, and it's very convenient because it's basically the exact species and size I was looking for. Got a few obstacles to cut it. Got power lines on both sides, conveniently the direction it leans. The process is going to be to cut it in segments and try and pull it away from everything. I believe that these are basically little kid shin guards for soccer that are zip tied to the metal, but I think for our needs it'll work. So this should basically just has 2 spikes and allow me to just dig in and climb up as I go. Probably get up to a certain height, and remember that I have a fear of heights, and we'll see what happens at that point. So I've gotten a lot of the tree limbs removed and cleared. Now a little bit of deliberation. I'm trying to figure out what to do next. It's a lot harder as it gets higher up. A lot more obstacles and a lot less confidence as the whole thing starts to wiggle. So after getting a closer look at the challenges involved in actually cutting my tree and not getting electrocuted, I opted to not risk my life and bring in a professional to take care of it. Big thanks to Peach Tree Care, a local Twin Cities-based tree removal service, who are pros at handling any tree from massive to small. Check them out if you need a tree removed or trimmed in the Minneapolis-St. Paul area. How long have you been doing this for?
I've been doing tree work for about 10 years. Kind of what we did was unorthodox, but effective. It was a tight situation with the power lines and stuff like that, so just got a rope in the top. We knew it was dead and really light, so we shouldn't do anything really crazy, but stuff we've been doing a long time, so we kind of know what we can and cannot do. We work in the Twin Cities in and around usually. If anybody needs any tree work out here, just give us a call.
So one issue we really have to deal with historically is high power lines potentially getting in the way of your tree felling. So I had some professionals come and take just a little bit off the top so we don't have to worry about that, and left the rest of the tree here for my own cutting. And for this we have the Viking axe that was forged. Of the axes we made, I don't think we've really tested this on a full tree, and this will be the biggest tree we actually try and cut. Before this we've done stone, native copper, and bronze, and they've each yielded better performance with each one, and I expect this one to probably very easily be the best. So this is a good over a foot thick, so it's gonna take a little bit, I think. Historically, when it comes to turning a tree into usable lumber, there are a few techniques we've explored in our past projects. Perhaps the simplest is riving, where you split a log along the grains of the wood. This works fairly well for straight timber without many knots, but doesn't produce perfectly square and straight lumber. The other option is hewing, where you effectively chop a log into desired dimensions with an axe. This was the standard method for producing lumber for most of history, until the industrial sawmill came in and supplanted it. But before the sawmill, there was also the option of sawing it by hand, which, to best get something comparable to a modern 2x4, is a process we'll be doing. The historical way to mill a log into lumber is either using a pit or a pair of giant sawhorses. which allows a 2-person crew to run the saw from above and below, slowly working your way down the length of the log. So we have our log put up on these nice sawhorses, giant sawhorses that Lauren put together to prevent us from having to dig a huge pit, which is the other method. This is the saw blade that we forge. This is supposed to be for the sawmill, but first we're going to use it for our actual hand milling. It's a little short for this. It should work, but just in case, I made a much bigger one. It's a little bit more appropriate for a 2-person team. So that should hopefully speed things up. Basically the exact same process to build it, just a lot longer. I made the teeth a little bit finer. So first step, we'll put a chalk line, get a straight line that will cut along, and that'll be eventually the bottom, and we'll square everything off of that. So we brace things, tied it off at the end, add some little platforms here just to be a little bit more sturdy. It's a touch wobbly, which isn't great when we're sawing on it, but I feel a lot better now. A little bit more. This was also left in the rain, so it's nice and wet, probably even harder to saw. Actually seem to be having better luck with the smaller saw. I think just because we had larger teeth and able to get a little bit more kerfing, which creates a bigger channel so the saw blade doesn't bind. That's the main challenge with the other one. A lot easier to use, but hopefully we get further enough in, we can add a wedge to split it out and kind of resolve that issue for the most part. But this is pretty slow going so far, and this is the end that has rotten, so it might get even harder as we go. Things are not going as smoothly as hoped. Seems the main issue with the big one at least is kind of the kerfing, so that it keeps binding and it makes it really hard to get a good full stroke. It is incredibly exhausting, and I don't know how much further we can go beyond this few inches, which is very unpromising. Rather than trying to power through it, it's better to kind of rethink, re-examine, make sure we get all of these teeth of the saws and everything set up in the most efficient way possible before we burn ourselves out. All right, so we're back at it for day 2 of the milling, and hopefully this time we have a little bit better success. So I went through and made a few improvements to the saw blade here. Basically doubled the size of the teeth, cut out every other one, and then was able to add some better kerfing to it to allow us to a little bit wider cut for the blade, so hopefully it shouldn't bind. And then as backup, got another saw here, some pretty large teeth. So I also did thin down the blade, and the unfortunate thing of that is when the frame falls out of the frame, you got pressure on it, it's gonna bend it back up. So it, as we were doing it, I think it got a little loose. The bottom pin came out, and then it got squished. So just have to straighten that out, get back in the frame, get things tightened up again. Should be good as new. A little crooked, a little trouble keeping it straight, but we're making pretty good progress. When you're in the bottom, you definitely get a lot of sawdust in your face, your eyes, and in your mouth, so that's fun. Yeah, got a little bit of curve to correct for, but so far we're about a foot in. So I think we're about ready to move the sawhorse out and just soften the middle and do the rest of it. Yeah. All right, so it took about 3 hours. So we got our first cut.
It's really straight.
Honestly, better than I expected.
Yeah. When sawing it, it looked super wonky.
Yeah, got pretty bad at the end. I think there's a lot of knots. Just overall, you can tell there's just a lot of knots in this thing.
Just don't look at that.
Yeah, we got to clean up the end a little bit still. Just kind of split at the end. It took three of us about 3 hours at least to do this first cut. That was with a lot of breaks. I think that's probably the main thing that slowed us down, is that very exhausting, and we had to stop and rest a fair amount of times. So I think if you're in shape and you got the motion down, it probably would be a lot quicker. But yeah, so that's 3 hours for one cut, and we got 3 more. So we are running low on daylight, so I don't know if we're gonna get our board done today. Each successive cut should hopefully be a little bit smaller, a little bit narrower. So hopefully it should speed up after this.
Less resistance. Hopefully it'll be easier. Show my snowman. Well, update on him.
What about the other one?
Oh, that guy? Oh, he was not rocking his glasses right now. But he is hitting the dude. Cool as hell. Oh my gosh. Yeah! Oh!
Close enough. Horn's dead. All right, so we got halfway there. We have 2 sides, and I think this cut is a bit straighter. This one went a lot quicker. What was it, a little bit over an hour?
Yeah.
The other one took 3, and it was still very difficult, and that's just because we're all really exhausted and can only go for short bursts, so that's slowed things down a lot. We're at like 4 hours now, I think, just to get these 2 cuts, and still got 2 more to go to finish the 2x4.
For the last 2 cuts, I opted to switch to indoors and sawing solo with a log clamped vertically, another method I've seen depicted in some illustrations. One more cut to go. After a lot of sawing to make all the cuts for our 2x4, and as you can tell, she's a little crooked. Not the straightest cuts. Got a little bit of curve here and there, and not even all that square. Sawing by hand leaves a lot of room for random variableness, and it's something that I think is a big advantage to the sawmill, is that it was a consistent mechanical repetitive motion that would produce a consistent result. Whereas this, you know, you get a little tired in one arm or another, you're gonna kind of favor that, and suddenly you're off. Even an experienced sawyer who's cutting boards, it's not gonna be spot on. It's probably gonna be a little bit wonky. But for any like fine woodworking where you actually want it to be perfectly straight and level, you're gonna be finishing it with a draw knife and hand planes to get it perfectly flat. And with that, I think I can just do a little bit of handiwork with a draw knife and whittle out an actual straighter 2x4 here. So try not to spend too much time, but try and clean it up a little bit and see if we can get a little bit nicer looking 2x4 out of this. So I did a fair amount of planing and draw knifing this guy. I think he's looking a lot better and a lot closer to an actual 2x4. Took out some of the thicker areas, so able to kind of average out some of the curve. And this is a much more promising 2x4, I would say. We have a kind of standard one here for comparison. It's a little bit thick, a little uneven, still a bit rough, passable for 2x4. I think I've seen considerably worse boards than this for sale at Home Depot. I'm gonna consider that a pretty good win. This is obviously a pretty learned skill. The better you get at it, the better your result's gonna be. But I think for a first attempt, I'm pretty happy with this. But how much did it cost? So the first cut on this took 3 hours, but that was with 3 people. So that's a total of 9 hours of labor. And the second cut was a little bit quicker. It only took an hour, but that was still with 3 people, so that's 3 hours of labor. And the third cut slowed down a little bit, we had 2 hours, but that was just by myself, so that's only 2 hours of labor. And then the last cut was only 1 hour. So that puts a total of 15 hours to mill this 2x4. If you're someone who's a little bit more experienced at this, you could probably cut down those hours. I wouldn't be surprised if you could do it in half the time. So today's minimum wage of $13.50 here in Minneapolis, Minnesota, that is $229.50 of labor just to produce this. Well, I was able to squeeze out a few pennies by cutting down the tree I owned that would already need to be felled. It ended up costing $250 to have the tree people come and make sure I didn't electrocute myself to death. That puts us at almost $500 for this 2x4. For comparison, during 2021, when timber prices got pretty crazy high, they were up like 500% of their normal value. A 2x4, which sometimes costs $3, was going for the astronomical price of $15. Mine cost almost $500. The exact price is $479.50 using the minimum wage here right now in Minneapolis. You might be wondering, why did I waste a bunch of time making a really expensive piece of wood? And the answer is, that's kind of what this channel is about. It's exploring the things we just kind of take for granted and trying to see just how difficult it would be to actually do it yourself. And the main set of rules is that I can only use things that I have made and effectively unlocked. And a big thing for a lot of future projects is having dimensional lumber and timber to work with rather than having to spend 15 hours on each board. And this also acts as a baseline for one of my large upcoming projects that I've been trying to work on for a while. I'm basically trying to industrialize and produce a water-powered sawmill. So thanks everybody for your continued support. Without you, this wouldn't be possible. Consider supporting us on Patreon. We're adding in some more voting abilities where you can kind of help direct what type of things we're making. Thanks again for everybody's support. Thanks for watching. One of the most important tools for the Industrial Revolution was a lathe. Earlier this year, I built one of the earlier forms of it, the pole lathe. The pole lathe is an amazing tool, useful for a lot of woodworking, but it also has its limitations. Because it works on a spring, it has to reciprocate and rewind between every press of the pedal. This gives a bit more of a challenging learning curve to master it, as you can only use it half the time it's spinning, and having to stop and rewind with the spring limits the speed of rotation you can achieve with it. With the goal of using it as a tool for industrialization, we're gonna need something with a bit more power that can achieve a higher rotational speed, as we're gonna want a lathe that's capable of shaping a wide variety of materials, from dried wood to eventually metals. And that's gonna require a bit more power. So for some visionary help to try and improve my current lathe design, let's look at some of the 500-year-old sketches of Leonardo da Vinci. Da Vinci is believed to be one of the first people to sketch the design of a treadle lathe. The key component to the lathe is the addition of a flywheel, as depicted in his drawings. A large, heavy wheel, it adds mass to the spinning of the lathe and allows rotational energy to be stored. So once the flywheel starts spinning, its inertia will help keep it spinning. Then is the addition of a treadle with a crank. When spinning, this allows additional energy to be added to the lathe by simply pumping the treadle up and down, allowing you to increase the rotational speed of the lathe to be higher and higher.
All right, let's make some lube. To really get some good motion with the wheel, we want to reduce as much friction as possible. And for that, we want a lubricant or a grease. Today, we're going to explore a little bit more advanced one that was supposedly used by the ancient Egyptians and ancient Romans, where you basically do very similar to soap making, but instead of using lye, you use lime with your fat, in this case, olive oil. You react the two and you get a soapy substance that is not water soluble. So for actually washing, it's not very useful, but for use as a lubricant, it's pretty good. So I'm basically just going to combine the olive oil with lime to produce our calcium grease. As I have a dried out lime, so first up we'll add a little bit of water until you get kind of hot. So now we can add the quicklime paste to our olive oil. Should hopefully dissolve and get us a nice grease. Then strain out the solids that precipitated, and the end result is this nice solution of calcium grease with the remaining olive oil, which can then be applied and used to reduce friction on any of the axles in our future build. All right, so here we have the Leonardo da Vinci Lathe. We have our treadle, we have the crank, and we have the flywheel. So the pole lathe has the disadvantage that you have to go back and forth with the spring. And this one is all continual motion in one direction. Once you get going, you get a pretty decent speed, and you can just keep pumping it to go faster and faster. And the real key to it is the flywheel, which helps kind of store momentum. And I've seen some versions of this that are even bigger. They probably work even better. So I made some improvements to the DaVinci Lathe. The biggest one is I made a giant flywheel that is more comparable to the size on there, and that's gonna hopefully give it some nice momentum in it. Kind of went a different style with the actual frame of it, just because before it was a little bit wobbly as it's picked up momentum. I think it's all set up. Takes a bit of effort to get going, but this is it. This is basically what he sketched. This is Leonardo's lathe, and I have to say it does work. The biggest shortcoming I'd say to this is that it's what we call a direct drive, that the speed of the flywheel is how fast our actual object goes when we lathe on it. So the biggest improvement you could make is turning this giant flywheel into a pulley to a smaller wheel that is then connected to the drive. Every rotation you do of this gives you multiple rotations of here, allowing you to go a lot faster. The main goal is to get higher RPMs so we can lay some harder woods and materials. But it's kind of cool to put this hypothetical drawing that Leonardo da Vinci made and actually make it real. It does work, and it's a little bit easier to use just because there's no like rhythm of having to do it on each push. This is one continuous motion. So these are all good improvements. But the next step is to do what is a more modern style treadle lathe that became popular a little bit later in history, where you use a pulley. So I did a whole second part of this video. That was the ultimate goal, and I have spent several weeks now I was able to repurpose the frame and the wheel that I made first. Able to get something that is really close to working. I'm finding that just like the little bit of complexity to it, just all the extra moving parts, that just every little thing, something could go wrong. A little too friction here and here and here, and then that's too much pressure, so then I keep breaking parts on it, and I think at this point I pretty much rebuilt it several times now, and it's still not quite working. I can kind of get spinning. It's going to take a lot more tweaking. Hopefully I can get a better working result in the future, and you'll kind of just see that tool getting used once it's up and running. The very next step after the treadle lathe, empowering it by foot, is to actually connect it to an external power source, such as a water wheel. Then we could really get some power and have something we could even do metal and stuff, which would be really important for a lot of upcoming projects, perhaps most notably the steam engine. I'm pretty confident we're gonna want a lathe for that. So thanks again to everybody for watching. Thanks to all of our patrons. I recently did a poll, and it's something I'm gonna be doing more this year, of just asking my patrons what direction they want the channel to go. And one of the first polls I did this year was what project you want us to revisit, and the lathe was the first result. If you wanna add your voice and your opinion and kind of help direct the channel and how it goes, be sure to become a patron. So if you enjoy this content, please subscribe and consider supporting us on Patreon. Thanks for watching. Manual sawing is hard work. With modern tools, it's easy to take advantage of all the quick cutting tools, from miter saws to table saws to band saws. But the mighty handsaw is capable of doing the same job. It's just a pain to keep it perfectly straight and perpendicular, and until you've really mastered that skill, it's a lot of work. I'm on a quest to build myself up from the Stone Age to my own industrial revolution. So I'm all about building some tools that will make jobs easier. In this video, I'm exploring the historic invention, the pull spring saw, and how it helped make this job a lot easier. It will be a key stepping stone for my ongoing sawmill project. In one of my earlier builds, I made a pull lathe. Connected to an overhanging branch, it was powered by a foot pedal with the spring power of a bent branch to reset it. Historically, a very similar concept was applied to saws. Where the lathe spins back and forth, the same motion of the foot pedal and spring allow a saw to be brought up and down. Without this device, you'd have to do the back and forth motion yourself, or with a partner on a pit saw setup. We did this previously to saw my own 2x4 from scratch and found out just how much work that is. Making those 4 cuts took 15 hours of exhausting labor and resulted in a very far from straight 2x4. This device not only helps make it a one-person job, but it holds the blade perfectly vertical with a perpendicular surface to guide the wood, allowing you to focus on cutting straight or to whatever shape you want. For the build of this tool, it's going to be 4 main components. First up is the actual saw and its frame, and fortunately we've already forged the saw previously in the initial video for the sawmill project, and then we built this frame when we used it in the pit saw. So this section is pretty much done and usable as it is. After that, the second part will be the body, is basically the frame that will hold the saw and provide a track for it to go up and down. Then also importantly, it'll have basically a flat surface. It'll be perfectly perpendicular to the blade that you can rest whatever you're working on, and that'll allow you to saw without having to worry about it being crooked. The third component will be the actual spring pole, and we could do this outside like we did the pole lathe and attach it to a tree branch, but another method that was often used was a bow at the top to offer the spring resistance. So I think we'll make a rudimentary bow for that purpose. But lastly is the foot treadle, which provides the power for the saw. So the first step of this is going to be sawing a bunch of wood, and unfortunately I'm going to have to do it by hand until we have this project finished. Alright, so I outfitted the saw with a little bit bigger one that I used for cutting the 2x4 before by hand. And I got scrap from the 2x4. We have some of the old cuts, which you can tell are pretty crooked. So we can put this to the test and see how much improvement this will make. This is also going to be useful for the eventual water-powered one. I think already doing a few cuts, I can tell that the fact that it pushes the wood up as you're cutting is kind of an issue. So I'm going to need to incorporate that into both this and an eventual sawmill, just so that we hold it steady. So I got the straight line marked on here. A similar cut by hand by myself took about 1 hour with this exact same saw. So we can give this a shot and see how that does. All right, so that was definitely a workout. Whew. But that is my first long cut using this saw, and that took less than 30 minutes. So we're already seeing an improvement in speed of at least double. And the cut actually looks pretty nice. I had a little bit of an issue keeping it straight, but in terms of square, it's a little off. And that's mostly because the reference to the bottom is also crooked. But that is, I would say, considerably better than all the other cuts I've done. The biggest issue I think that slowed me down is when it would bind. The big challenge is just kind of getting a feel for it and like how fast you can go. It seemed the faster I ran it, as long as I kept it pretty slow, it wouldn't bind. It was very hard to gauge that because it would then bind pretty quickly. So I know a lot of water-empowered sawmills have their own kind of ratcheting feeding system, and I can see how that's important because you're able to adjust it to the correct speed of the saw itself, and then just kind of consistently do it and you never bind. Definitely something to keep in mind as I move forward with building an actual sawmill. And overall, I have to say I'm pretty impressed with just how straightforward this project was. The last few ones I've done, namely the lathe I made before, was just a lot of little things that prevented it from working smoothly and correctly. Where this thing is actually nice and straightforward, and I was able to get it pretty much right away. Feels like it's almost unexpected where something actually works on the first try. It is a giant beast though. It's almost to the ceiling and it makes it a little bit hard to move around. So I think this is both a useful tool and also gonna be a very important next step, which is saving myself the actual labor of doing it and finding a way to hook this up to a water wheel so we can actually have our sawmill and then fully automating things like the feeding of it into there. So we basically just set a log in there, let the water power it, and we'll have a cut where we're not working up a sweat. So my first manually cutting of the 2x4 cost around $500. With this cost-saving device, we could probably easily cut that in half, probably more. So I think with a little bit more practice on here, I could probably get this down to at least 6 hours and maybe a $200 2x4. It's getting closer. We aren't yet beating the Home Depot price, but the next step with the sawmill and the water wheel, we can actually get down to comparable price. Thank you again to all of our supporters on Patreon. Without you, this wouldn't be possible. Thanks for watching. In this video, I'm recreating one of the most important inventions for industrialization, the water wheel. With this device, you can harness the power of nature and flowing water and use it to power countless tools. Tools that before this, I would have to physically operate myself. So let's start saving some of my sweat and hours of labor and harness the power of nature. If it hasn't been clear from my previous projects, manual labor is a lot of work. So finding a way to power tools that's not limited to my own endurance and strength is going to be a huge multiplier when it comes to getting things done. Just operating a handsaw gets very exhausting pretty quickly, but with a mill connected to a water wheel, even if it runs very slowly, it can just run continuously without ever getting tired. I've already built a few tools now with the intention of connecting it to an external power source like a water wheel, and have a few more along the way just waiting to take advantage of this power source. The design of a water wheel comes in a lot of varieties, shapes, and forms. You could even argue that modern hydroelectric dams are a form of the modern water wheel. For how important this device is for my goals and the wide variety of devices I'm hoping to power with it, it's pretty likely I'm gonna have to build at least a few different versions of water wheels. So rather than kind of getting down into the very specifics of this, it seemed a lot easier to just start with a simple water wheel and kind of learn as I go. Test it out, see what is and isn't working, and how I can adjust it and make improvements to it from there. But this technically isn't even the first water wheel that I made. I actually started another project attempting to harness the power of animals by attempting to bring back the historical job of the turnstile dog. The wheel I built for that was hopefully going to be reusable as the first draft of the water wheel. Trying to harness the power of a dog is proving to be a little bit more challenging than I expected, and I'm still working on that project, and that wheel is not available to be reused yet. So I looked at a few different options of wheels and found a really straightforward and simple one that had some nice features that made it a little bit easier to build. Mostly the bottom of the buckets is also the paddle, allowing it to be one continuous piece and a little bit easier and fewer parts to assemble. When I look at other forms of water wheels, they often have a lot more paddles, so I think that's gonna be probably a really easy improvement to make, is to add more. So with the design in mind, now I just need to cut up a bunch of wood. Unfortunately, I have to do it by hand because I don't have a water wheel yet. In one of my previous videos, I made this pretty nifty machine for cutting wood, and has a frame saw inside of some rails here with a spring on the top, so with a push of a lever, you push it down and it springs back up. So it makes a pretty powerful 12th century table saw that is really useful for making straight cuts, making a little bit less work. However, this is really only set up for rip cuts, and I have a lot of cross cuts I need to do. Because when you have to cut it with the board, you'll start to hit the side rails. So what we really need is a different type of frame saw on here. And for making rip cuts, you have the saw blade in the center, and then you cut along the length. For a cross cut, you need arrangement more like this, with a saw blade on one side, middle bar to hold it rigid, and then a tensioner rod here. So my thought is basically attach a saw like this to the frame running this way. So then we have the blade out here. We can extend our cutting platform, and then we can cut it sideways. Obviously, the most challenging part was finding a body of water at high enough elevation and then finding a way to pipe it all the way to my property using a series of bamboo tubes. Obviously, that's what I did. Pay no attention to that high-pitched whirling noise or any suspicious tubing. It's very satisfying to finally get this project together. It's something that's been in my plans for several years now, and it's definitely now the largest project I built. The actual engineering of it was a bit more challenging than I originally expected, trying to keep it all evenly constructed and jointed together, and the matching between the two sides of the wheel took a bit more work than I initially planned, and even then I still had to seal a bunch of gaps in the wood for it to run pretty well. But now it's all together, and I have my next major step towards my own industrial revolution. I tried connecting the water wheel to my saw using a simple crank and connecting rod, but that didn't have too much luck. I think I really need to find a way to connect it at the top or the bottom of the actual saw, otherwise it pulls and binds in the frame. So the next challenge is going to be all the gearing and such to effectively connect my tools to this power source. So with this tool, I'm now able to harness some of the powers of nature and use them for my own use. Unfortunately, sometimes when you try to control nature, it fights back, and ran into the metal rod that's sticking out for the axle of the water mill more than once. That's a really embarrassing part, is that I did it once, kind of called it a day, picked it up the next day and proceeded to do the exact same thing and hit my head again and leave an even bigger scratch. That was fun, but like as I said, I've been anticipating this project for a while. It feels like one of the major stepping stones for the Industrial Revolution is getting other sources of power and figuring out how to gear and utilize it like this. So very excited about this. Lots of new options opening up. Some of the next projects will be making improvements to the water wheel and getting it connected to different tools and start to use that power source. I do want to eventually, once it's all kind of figured out, bring it to an actual river source, generate actual power, hopefully actually build some sort of generator that connect to it with our wheel, and then have an actual hydroelectric power plant. And I'm hoping there's enough time before the end of the year to do a windmill as well as another source of power, and maybe even possibly start getting into solar. So lots of possibilities opening up with this. Thank you to all of our supporters on Patreon. We wouldn't have made it to this milestone without you. Thanks for watching. Pretty much everything we use today comes with some level of production, extraction, and refinement. For most of history, this had to be done by hand and made most items pretty expensive and labor intensive. But today we can buy so many things for a very cheap price. Do you ever wonder how we got to where we are now? In this video, I'm going to explore one of the early human technologies that first helped to reduce the cost of labor and make things a bit cheaper. Using some inspiration from inventor Leonardo da Vinci, I'm going to attempt to build a water-powered machine that will automatically mill a log using just the power of water. So let's try and build this machine and see if it'll actually work and make my first baby step towards my own industrial revolution. Milling wood is a lot of work. And I did my own video on this, kind of exploring just to see just how difficult it was. Needless to say, it was a bit exhausting and slow. So it's not that much of a surprise that some of the first industrialized machines were for the purpose of milling wood. Historically, a few versions have existed throughout time. Mine, I'm going to take a little bit of inspiration from inventor Leonardo da Vinci, who drew a rough sketch of a design in 1478. The drawing is pretty rough, and it's believed to actually be based on some earlier drawings by some other artists, but does provide the inspiration for a pretty sophisticated sawmill. And this is going to be basically 5 components to it. First up is a water wheel, which will provide the actual force to the machine. Second is going to be a support structure, which is basically going to hold the saw and everything up above the wheel so we can have mechanisms below it. Then there's going to be the actual saw, which is in a frame, and then the track that slides up and down. Below that is then going to be a crank mechanism, which turns the rotational force of the water wheel into a reciprocating motion to bring the saw up and down. There's going to be a sled that the wood sits on and that is slowly pulled through. And to actually pull it is going to be a ratcheting system to slowly pull the cart bit by bit through the saw. At this point, I've been able to do a few projects and knock out a few parts of this. Most notably is the water wheel, which I did in a previous video. So that's pretty much ready to go. Compared to his design, my wheel is a lot bigger and has actually an overshot rather than undershot. I think this should all give me some advantages with power. Then another piece I already have, which is actually the very first project in this series of making a sawmill, and that is the actual saw blade that we forged before and then built into a frame. So that gives us a nice starting point with the wheel and the saw frame. So next up, we just got to build a main support structure, which will be be kind of the skeleton of this. We'll attach a wheel to it, set that up as the main structure, and hopefully we can get this thing to work. We have a little bit of new technology that we recently unlocked. Thanks to some help from some new assistants I have with Elliot and Theo, we were able to build a nail header, and that allows us to mass produce nails a little bit quicker. And thanks to them, I was able to get a nice supply of nails to use to help hold everything together. So I have kind of a rough layout of the wood for the frame here, and basically what I'm making is more or less a bed frame. So we have the legs here, I'm gonna elevate to the right floor, and we're gonna have an outer frame here. To get this really secure so we don't need to brace it too much with wood, I'm going to use some joinery in combination with nails rather than just straight nailing, and that should give us a tighter fit and hopefully something pretty solid that we can stand on and work on. So what I'm gonna try and do is called a castle joint, which is often used in furniture, which seems fitting for this. I have basically cut 3 different joints to form a corner at each one, and it should produce a really strong hold, and should hopefully get a pretty strong result. So I have all the joinery cut for all the pieces of wood here, so everything should hopefully, in theory, snap together and form a pretty strong base. We have the castle joints here. These will intersect each other. And then we have the legs, the 4 points, and that will insert into there. And we should have a pretty strong platform to hold it all together. We got some nails we can throw in there to really hold it up, maybe even throw a little bit of glue.
Somewhat stable.
Yeah, a little wiggly.
Whoa! That was loud.
Jeez, that's startling.
We've forged out some small 4-inch shafts. One end we have upset, so it's a little bit larger diameter than the rest of the shaft. On the other end, we drew out into a small nub. So the idea is we've made a bunch of these little washers here. Washers, second washer, and then we can bend over this nub and lock everything in place. We'll see how it works.
right, so we got this all rigged up for the crank now. Took a little bit of jerry rigging to get extra braces for the axle. I think we should be pretty much set to give it a little test run. Took a lot of tinkering to get everything to just kind of align just right, but at this point it should spin and push up. Up, and then back down. Wow.
Oh, yep, see the hooks walking?
Oh, wow.
It's easy fix though, we can put. We basically have a wooden axle that runs through the entire frame of the device. We've got our ratchet in place, and then we're essentially just going to assemble everything into a basic fulcrum. So we start with our long arm here, and we have a pivot here, and then the drop arm. Right in like that. And the idea is the arm will come down and just very slowly increment the ratchet.
Just did a test run of it without a log in there, and everything looks to be going pretty good. We have some small issues that could potentially be a problem. We had to add this little kind of lock on the ratchet just so it doesn't backspin. There's a little bit of play with the wheel, the lock, but I think once we get it pretty good, it might require a little babysitting, but for the most part it seems to be working. I think we tried to mostly use wood components, which is pretty historical, but there are some parts we might eventually find we need to redo in metal. Everything actually works pretty good. It's honestly pretty surprising for kind of simple design, but it's like complicated enough. It's actually kind of impressive, I think. Might be a little bit of fine tuning, but I think we pretty much got it here. So just put a log in there and see what happens. Suspense is killing me. Once the log finally reached the saw, everything seemed to run smoothly. Overall, the cutting was a lot slower than I expected, but the saw slowly made progress through the wood. I think optimizing the speed and rate of cutting is something that can only be done with a fair amount of tweaking to the design, trying to get just the right amount of tension on the cutting surface versus putting too much pressure on it and causing it to bind. Making all these tweaks is probably only going to be possible when it's fully running, and however, the largest challenge turned out to be the components I didn't build. The water pump that simulated our power source, a rushing river, proved to be difficult to keep running with a consistent flow. Leaves and other debris kept clogging it, slowing down the flow, or straight up stopping the water. It was a bit chaotic trying to clear it, get the flow back up and running, and ultimately the pump ended up burning itself out in the process. So ultimately the machine ended up running pretty slow, not the most efficient, and my river kind of ended up breaking. But all things considered, I think I would call this a success. We've been able to put together a relatively complex machine based on just a rough sketch from several centuries ago by DaVinci, and all the components actually work. It's a little disappointing that the whole river ended up breaking down before we could finish the log. It did progress enough that we were able to tell that it is working. While it is running pretty slow and it would probably take a while to actually saw the full log, the main advantage with the sawmill is that you're not really wearing yourself out. If you were to do it by hand, you could probably do it quicker, but you're gonna get tired and not be able to do it all day. Here with the sawmill, you can just run this thing continuously and it's never gonna get tired. So ideally we hopefully can speed it up. And I think that's just kind of the relationship of the different components of the ratcheting wheel and how fast it pushes it through and how much pressure and how fast the saw can go. So I think the issues with the speed are probably more just based on the interpretations of the drawing that I did. And I think just some tweaking, we could actually get it to work pretty good. And the issue with the river kind of basically running dry is actually probably kind of fitting because a lot of river sources would be seasonal. And the best time to basically run your mill would be in the spring when a bunch of snow melts and you get really strong flow. Right now we're entering into fall after a bit of a drought. If this was set up for real, I likely wouldn't be able to run it now anyways. That being said, I did design the water wheel to fit onto a trailer so that potentially could move it to a water source and get it running. Actually finding one where it can actually transport it and put it there is easier said than done. So gonna be an ongoing search and it might end up being something that I can only do in the spring at a certain location. So the hope is at some point to get this actually plugged into a real river. I'm gonna have to do some tweaking and redesigning to try and find a better way to simulate the water and hopefully you can get a little bit more consistent and long running result to actually mill some logs. Very impressed with this result. This is a surprisingly complex machine, very much the largest project I've built, and the fact that it runs as well as it does is just kind of fascinating. It's both simple and complex. So it's definitely a really interesting topic to explore, and I hope to make some more industrial machines pretty soon and see how advanced we can get with this. Thank you again to all my supporters on Patreon. Without you guys doing these more long-term projects, wouldn't be possible. So thanks again, and thanks for watching. Previously, I attempted to recreate a water-powered sawmill designed by Leonardo da Vinci from 500 years ago. Da Vinci is famous for his many designs and sketches of various machines, weapons, and mechanisms, some of which predicted inventions yet to happen centuries in the future. But drawing a rough sketch machine that can work in theory and then turning it into a mechanism that runs continuously and smoothly is a whole other challenge. At the end of my previous sawmill video, I was able to establish a basic proof of concept. The Da Vinci's design worked and the water-powered sawmill would cut. But in the end, we only achieved a few inches of cut lumber before my artificial river ended up breaking. In this video, I'm going to explore the difficult process of trying to turn this concept from theory to practical reality and troubleshoot all the problems with the mill until I can successfully achieve a complete cut piece of lumber. Perhaps the best way to figure out how to make a working sawmill is to visit a working sawmill. So I did that. I actually did this a few years ago when on a whim on vacation I was able to just barely catch the end of the demonstration of a working water-powered sawmill near Mackinac, Michigan. Comparing this working mill to the recreation that I built, there are a lot of very obvious similarities. The rough idea is basically the same. Reciprocating saw blade attached to a wheel that is spun by water, which also pushes a ratcheting system on a sled to slowly draw the log through the saw. But there are also some distinct differences. The largest difference is probably that they have an actual real water source, a dammed up stream, which they can control how much water is then released. And when they open it up, a ton of water comes flowing through, spinning their wheel like crazy. They have a little bit different design of a water wheel, which provides a much higher spin to theirs, and it's connected to a vertical axis with a geared connection to the actual saw. Their saw is huge compared to mine and has a large, distinctively shaped hooked teeth. When powered, it is quite fast and forceful owing to all the water flow they have at their disposal. The ratcheting system is a bit more complex than mine, with much finer ratcheting teeth, and the lumber sled is fully enclosed so it can't bounce up and down. My favorite part is the placard about the designer of the mill, who was able to take off and just go fishing while the mill did all of the work for him, which really drives home the whole point of this technology, freeing yourself from hours of manual labor. So obviously a lot of that I won't quite be able to implement, but I can at least apply a few changes based on what I saw. Plus, I got a lot of helpful suggestions from the comments in my previous video, and I can go through and try and implement at least some of these. However, the especially challenging part of this next step is that it's going to be against a bit of a deadline. This fall has been unusually warm so far, but winter is quickly coming. And I live in Minnesota where things are about to get very cold and frozen before you know it. So the challenge here is to get things up and running before the weather turns too cold and freezes us out. Let's see if we can get this log cut. So we made a few improvements to try and get this sawmill working a little bit better. We added 3 times as many paddles to it, which I think will allow it to get a little bit more consistent of a spin, hopefully. We added some kind of splash guards to try and retain some of the water that splashes out. Then we built the giant water tower. We now have 2 pumps. They're pumping the water up there at the same time, and hopefully that will provide enough flow.
Fair enough.
Now we're kind of dependent on the volume in there. If it gets too low, the pressure drops and we lose the amount of speed and torque our wheel is going to have. But hopefully the pumps will keep it pretty consistently filled. There'll be a little bit of balancing act there. We've swapped out the blade with one that's a little bit thinner and more of the right profile for cutting like this. Should hopefully cut a little bit better at least. Also has more chance of it binding though because it's thinner. We had this middle joint here, middle bar that broke. Previously it was made out of wood, so that's now metal. A few of the joints here are redone in metal. And we thickened up some of the wheels so it stays on the track a little bit better. And I just have a ratchet on here for now. Eventually we want to figure out the dog system for holding it in. Just for testing purposes, we have the ratchet on there so we can get in nice and tight. I think we're looking pretty good to doing some more test runs and hopefully we can have some success. I think we're going to do it without the ratchet system first, figure out the cutting and how much pressure we actually need to put on there, and then figure out how to time it with the ratcheting so it isn't going too fast or too slow and we're just getting a good consistent cut. So I think we'll turn it on, see what happens.
More pumps.
More pumps! All right, so we're on 2nd or 3rd day now trying to get this to work and ended up forgoing the water tower. Ended up causing more difficulties just because the rate of flow would change as the volume of water in it would have a different amount of pressure, so we'd have to kind of adjust as we go. And it all just seemed to come down to the same problem of getting a consistent flow of water back in there as fast as we were using it. We also had trouble getting it up that high. So lowering it a little bit lower and going directly into the spout again made things a little bit better. So we have 2 pumps now going and powering it. We've been able to get a pretty consistent flow, and with all the kind of splash guards, we're still losing some water, but we are pretty good supply. I think the first time we did this, it ran itself out in less than an hour and you had to basically refill it from all the water splashing everywhere. So we got a pretty consistent flow of the river. It does seem to struggle at some points that maybe another 3rd pump might help overcome and add a little bit more torque. But beyond that, we've been sawing pretty much most of the day and it's been very simple. We don't really have to babysit it anymore. We got a pretty decent flow. We had a few issues that came up, not having much success with the ratchet, and we went to a weight system and trying to get the right amount of weight and pull on it, keep it advancing and cutting at a decent speed is a real challenge. Kind of check up on it every once in a while and give it a little push, but if you push just a little too hard, it'll bind up and the wheel will stop, the cart will lift up, and I'll have a lot of issues. We're able to get an inch in 10 minutes. It's still pretty slow, and it's a pretty slow process. Still have a lot of issues to still work out. The saw blade is cutting a little bit crooked. I think there's just not enough tension holding it tight. So I might need to add like a threaded rod or something to be able to really crank it tight. Unfortunately, because the saw blade does not go a full frame, we weren't able to put wedges in there to hold it extra tight. So we have a little bit of a drift to the cut, unfortunately.
which I was not expecting with the sawmill. I thought it would actually be just default to straight, but I guess kind of the same issues you run into doing it by hand you run into with the sawmill. We're making a lot more progress, but it's still very slow.
To help improve the straightness of the cut and hopefully improve our cutting speed, I ground a new saw blade based on the saw blade I saw in Michigan, which is overall just a lot thicker. This blade is a lot more aggressive. Hopefully I can capture enough torque to fully utilize it. Ow! I think it's sharp. Alright, so we did a test run here and got a lot of resistance. I think it's because the saw blade is slightly offset from the frame, so it's pulling it too far over. So what we did is we added a second frame on the outside of the track to kind of balance the tension between two frames. So that should keep the top and bottom pieces more in line with the track and not twisted. So hopefully we can have some success now. So we'll turn the river on and see what happens. It's a lot better. Think that did it? Pulling it in. They're touching now. A little bit of resistance. Good so far. A little bit more resistance. The new saw seemed to work a lot better, but was still struggling with getting enough water flow to power it without things binding. So might just take a couple more tweaks and we can get this thing running.
We may have overwatered your lawn a little.
And my dirt. The last few improvements I made to the sawmill seemed to make kind of the biggest difference. I ended up swapping it out with a much larger blade, and I don't know if the teeth made a huge difference, but I think the thickness of the actual blade definitely made it go a lot straighter. That in combination with a system of using threaded bolts that I could tighten, that has really made it just cut perfectly straight, which is something I couldn't even do by hand. And then one of the other things I did, I just bought like another fourth pump to just push us over the edge. This one's even stronger than the rest, and then kind of came up with a better system of preventing clogs, so you're able to run it a lot better without any issue. But there is still kind of a balancing issue I ran into a lot with this, is just getting just the right amount of torque, because you want it to cut as fast as possible and just put just enough pressure on the actual log. But if you push it a little too much, then things start to break. The most frequent place that it breaks is the shear pin, which connects the axle to the water wheel. And I've swapped it out with a few different metals and bolts. They either snap or they just wrap all the way around the axle. Eventually put it in with some hardened tool steel, and that so far seems to be holding up pretty well. And in the end, it took about 6 hours to cut the full cut. That's once you subtract all the breakages and fixing and tweaking, which overall is not that bad. It's definitely slower than doing it by hand. We did a 3-man team to hand cut a saw, swapping out with each other. That took us 3 hours. So it's about half the speed as a 3-man team, but when you factor in how many man hours that actually is, it's a bit different. That's 3 hours times 3 people versus 6 hours times 0 people. So it's still a little bit of an experiment to find the right amount of tension to put on it. But the weight system right now seems to work pretty good. It's easy to adjust. Never really got the ratchet system to work perfectly. It always just seemed to just put too much pressure, bind it up, and cause it to break. It took over a month now of just tweaking again and again and again to try and get things working. I think with more water and more force, we could definitely get this up to be faster than a handsaw. Every cut after that, when cutting the lumber, should go quicker like it did when I did it by hand, just because there's less material. So there's a lot of expense to this very first cut that we did. Ballpark, it was 126 hours of labor between 3 people to build the sawmill, and then it was probably 48 hours of tweaking to get it running smoothly as it is now, and then let's say roughly $500 worth of materials to build everything, all the wood, all the nails and the metal for that, the axles. It's about $2 grand to get that very first cut to the sawmill. But the second cut will be pretty much free. So our backup plan, if we couldn't get like a river to actually flow and power this, was, maybe do something really drastic. A lot of people suggested like we build this giant human-powered hamster wheel to power it. And unfortunately, we didn't have to do that because like that'd take a lot of work to build one of those. So good thing we didn't have to do that. But anyways, that's actually going to be a video coming up here pretty soon. Uh-oh. It's very satisfying to get this very initial step to the Industrial Revolution. Hopefully we can get to the steam age here in not too long. So thanks again for watching. Thank you to all my supporters on Patreon. See you later. Running on a treadmill is hard work, perhaps even torturous. But the first forms of treadmills date back to a form of punishment, and even further back as a form of power. In this video, I attempt to build this ancient technology and see if I can harness it to power my own tools. In my last couple of videos, I explored the water wheel, a way of harnessing falling water to power things like a sawmill. Unfortunately, water flows are very seasonal, with mills often only running during the spring when there's a high flow of water, and completely shutting down if you get below freezing. And that is on top of the limitations of only being able to operate one in specific locations with proper streams. When we were struggling to get our water wheel to spin, we resorted to manually moving it ourselves, which quickly gets exhausting. It doesn't take long before you try to optimize your labor and turn your water wheel into a treadwheel. Perhaps surprising is that some of the earliest forms of the treadwheel were basically used as reverse water wheels. Rather than being powered by falling water, human power was used to raise water. In this case, to pump water out of deep mines. The need to pump water from mines is a very important thread to follow when it comes to technology and history, as it's going to eventually become the impetus for the invention of the steam engine. But before I took on building this giant human-sized treadwheel, I actually built some smaller versions that I was hoping to do for a video to come out before that, where I actually harness the power from some dogs. Unfortunately, training dogs is actually proving to be a little bit more difficult than I had hoped. I'm still working on trying to finish this video, but the language barrier with the dogs has definitely proven to be a challenge. To build our treadwheel, we're basically going to need to build a pair of rings and then connect them to form our walking platform.
We're going to need 4 concentric rings in the shape of a dodecagon, otherwise a 12-sided circle. Each joint is going to be 30 degrees, so each cut on the wood will be a 15-degree cut. And hopefully, if our math is correct, that will form our dodecagon. So we'll see how it goes.
The rings outside and completed, we added the cross beams on them that would connect to the central axle. Then notched out sections to attach some cross beams to connect the two rings.
Have we established that it's very big yet today?
Very big.
We debated rounding off the rings to actual circles, but that felt like it'd reduce the structural strength. And keeping on the corners didn't seem to cause any issues with this design. Then it's just a matter of nailing in all the boards to form the walking surface. Next we need the axle, which was designed to fit snugly between the cross braces. The ends would need to be rounded off so we could spin it inside the supports. Lastly, just need to construct the supports. They'll hold it on either side. So I think we got pretty much everything together now to put it on the actual axles and get it spinning. So it's kind of scary. I think this is probably the first project that's really felt like if we lose control, it could run over and kill somebody. And it's a size I planned on, but in real life, it's a lot bigger than expected. Hopefully 3 of us can lift it up and put it into the side holders here. We're gonna lift it up on some car jacks here to get it up. These are rated for, I think, 13,000 pounds. So if it breaks that, we'll know this is at least 26,000 pounds. On the side supports here, we have this kind of block here, is so that you aren't splitting the wood here. Also is kind of a point where it's gonna wear the most. So as it wears out, we can swap it out with a new block and not have to rebuild the entire thing. So hopefully that works well. We'll have to grease it. It's also kind of triangularly shaped, which is kind of intended to hold it in place with a minimum amount of points of contact. Hopefully we can get it to work. All right, moment of truth. Time to get in, be the guinea pig. Ugh. Whoa. Oh. I want to be on this side. It moves pretty easily. Oh yeah, I can see how this gets you dizzy.
Kind of dizzy just a lot.
Ooh, that is, oh wow.
What have we built?
It's so much faster when you're inside.
Uh-oh.
At least it didn't go all the way around.
The use of the treadwheel as a source of power would diminish as the Industrial Revolution would eventually provide cheaper and more versatile power sources. However, the technology took a slightly different turn in 1818 when the treadmill was introduced as a form of punishment in prisons. It would still be used as a power source to sometimes mill grain, but other times it wouldn't even be utilized and was just a form of punishment where prisoners would be forced to walk the mill for up to 10 hours a day. And it was eventually banned by the end of that century. In the 1900s, the treadwheel was once again reintroduced with yet another purpose: exercise, and eventually evolved into the modern treadmill you find today at the gym. But this time around, it uses power instead of producing it. All right. All right. Takes a little bit to get used to. It's a little bit challenging to focus where you need to go. Gotta focus away, otherwise you get a little disorientated and a little bit nauseous. But I have to say the center beam is kind of right in the way. It's almost kind of nice to walk backwards and hold it from the post. There's a workout.
You're not actually gonna make me wear this, are you?
Don't forget the hood. There we go. Today, most people will compare the treadwheel to the hamster wheel, but really, the human-sized treadwheel design dates back to early antiquity. Hamsters, on the other hand, were really only domesticated as pets starting in the 1700s, not really becoming popular until the 1930s. The first reported use of the phrase hamster wheel wasn't until 1949. So if anything, this is a human wheel. So we were able to get the treadwheel built and it actually came together pretty well. A lot of concerns. It's just massive. Running it is a little bit nauseating, I have to say. Your eyes kind of sticking to the wheel, which is spinning, and the world that isn't gets you a little bit nauseous if you do it too much. And it really helps just kind of look off to the side and focus on something. Then you can run pretty well. And the center bar is kind of a little bit in the way, but it actually works pretty good. And it's pretty easy to just walk in it and provide power. It's a lot easier than just trying to manually spin a water wheel or something else. So you can definitely see the value of these and how they kind of came into use. So these wheels were used to power a variety of different things, from pumping water to grinding corn. One of the main things that it was used for is to power a crane since Roman and medieval times, where it could be used to lift a pretty substantial amount of weight. So we're actually going to be doing that pretty soon here to convert the treadwheel into an actual Roman crane and see how much we can actually lift with that. Other things the wheel has been used for are things like the trebuchet, which was used to wind it up and store the energy that you're going to use to fire it, which is a large project hoping to get to at some point and build our own trebuchet. But for this video, I thought we'd go back a little bit to an earlier project, the DaVinci cam hammer, and see if we can connect that to the treadwheel and power that, and basically have a human-powered power hammer. useful tool that can be used in a variety of upcoming projects, and really excited to see what we can make with it next. Thank you to all of my supporters on Patreon. Without you, I wouldn't be able to keep doing this. Thanks for watching. Rome wasn't built in a day, but compared to previous empires before it, like the ancient Egyptians, it had a massive advantage with just one single tool. The pyramids were likely built by manually dragging 2.5 to 60-ton stones into place, potentially requiring teams of 8 to 170 men to move them. Roman engineers, though, through the exploitation of a few simple machines, made it possible for a single human to lift at least 70 times their own weight. With this machine, a single person could lift a 7-ton adult elephant using just their own power. In this video, I'm going to build one myself and see just how much we can actually lift. Today, a modern large construction site is incomplete without at least one crane, a crucial tool for moving heavy loads. While modern ones are powered by conventional engines, the utilization of the crane traces its origin back to ancient Greek and Romans, where it could be powered solely by humans to move massive objects. But without an engine, how could such heavy loads be moved by just a single person's strength? Well, thanks to the power of simple machines. Simple machines allow mechanical advantages to multiply the force applied to it. These simple designs have shown up in a few projects I've done before. I've made lever-powered machines, utilized the inclined plane, wedges, and even carved my own screw. I even snuck in a simple pulley into our sawmill. Then of course I also did a project where I made a wheel. And I made another wheel. And then another wheel. And another wheel. And another wheel. And then another wheel. And yet another wheel. And another. And then another wheel. To maximize a crane's potential, we're going to utilize two main simple machines, the wheel and axle, and the pulley. So the overall main components of our Roman crane are going to be the treadwheel, a wheel that basically acts as a giant lever, the crane structure to give us a point to lift from, a set of pulleys which can act as another huge force multiplier, and then the rope. Perhaps the most straightforward element, but in the most literal sense, it is the element doing the most heavy lifting. If our crane fails, it's probably going to be because of the rope. In our last video, we built the largest component of the crane, the treadwheel. With some crane designs of this period, they just used hand cranks, but a treadwheel offers some huge advantages. A hand crank is limited mostly by one's arm strength and how much space you can afford to make the crank arms act as large levers. The treadwheel, however, works as one giant lever. To turn it isn't so much a matter of strength, but of repositioning someone's body weight to cause the wheel to spin forward or backwards. Our wheel is big, over 10 feet tall. And it's even large enough that with a heavy load, we could potentially have 2 people in at once, if not more, to add extra lifting power. So there are huge possibilities of lifting ability here using just this wheel alone. However, that's not very useful if we don't have ropes that can handle the weight. We previously explored basic rope making by hand using a simple hand braiding method. This makes decent rope, but as bigger and stronger ropes became more and more important, some simple machines were historically utilized to speed up the process. So it felt crucial to explore these methods and see just how strong of a rope we can make. Starting back at the initial fiber, we can go back to the original fibers we found from one of our favorite plants, the cannabis plant. These plants grow pretty much everywhere in Minnesota as so-called ditchweed, but it's really a variety of cannabis that was grown during World War II for hemp production.
So we've got the hemp stalks here that have been soaking in water for about 10 days now, and they've rotted a little bit in a process called retting, and that's going to allow us to use this tool called the brake to separate the wood fibers from the kind of long strands that we'll actually be using to make the rope. How you do that is by putting the fibers in between here, right on this little notch, and then hammering it and breaking it up, and that will help separate it, making it easier to pull them apart. What we want to do is get all of the wood parts detached, and then we can get the fibers and start winding them together into a rope.
Then the remaining woody bits are beat off. Let's rephrase that. Then any remaining woody bits are knocked off the fibers with a paddle. And lastly, the fibers are ran through a heckle comb to further separate any remaining bits and to align all the fibers together. Next, we can start spinning this fiber into yarn, which will then be the initial starting material for making rope. In contrast to the braided rope we've made before, we're going to make a machine to produce what is known as twisted rope. To keep these strands all together and from unraveling, each strand is twisted one direction, while the combined rope is twisted the opposite. This causes a balancing of the twists, keeping everything together as a stable, unified object. So we need a machine that can twist each strands independently and also the entire rope at once.
So this is what we've come up with so far. We're currently going with a basic 3-hook device. We're not quite there yet. We've gone through a lot of struggles along the way. Originally we had a wooden shaft and we've since upgraded to a metal one. You can see some of our various design concepts along the way. The biggest issue right now is we've got everything assembled, but it still jams pretty frequently. We're not quite sure how to overcome that. Here's some of our various attempts at different gears as well. You can see we have different spacing, different attempts at basically the same thing. But it wasn't for lack of trying. So we're getting there. We'll figure it out. It's just going to take some time.
After struggling a lot to get the gears to operate smoothly, we eventually decided to abandon that method altogether and switch to a belt and pulley system. This proved much more successful. However, this kind of feels like a bad omen for challenges we will face in the future with more sophisticated designs that are likely going to involve a lot of gears. It's likely we're gonna have to take a bit of a side quest in the near future to figure out how to develop methods of more precise machining to achieve these kind of builds without this much struggle. With a now working machine, we can begin the rope making process. Hemp yarn is ran between the two sides of the machine, and by twisting each side in opposite directions, we are able to slowly form the twisted rope. Then it's a matter of repeating this several times to produce 6 strands of rope. From here, we can repeat the process with these ropes to braid an even larger and stronger single rope. Each strand of yarn in this rope supposedly holds about 20 pounds. The final larger rope is 6 strands of the smaller rope, each made up of 6 strands of yarn. Potentially, we have made a rope capable of holding around 720 pounds. While the Treadwheel offers a large force multiplier on its own, we can maximize this even further through the use of pulleys. For our crane design, we're doing a tripostos crane, so named because it uses 3 pulleys. So let's construct 3 pulleys, 2 of which can be stacked together in a single block. Now for the last part, we just need the actual crane arm from which we will lift. The structure is surprisingly simple in Roman designs, oftentimes just a large triangle held in place with staked out lines.
Oh my god! This is terrifying. Look at that!
Time to start using the crane and testing its capacity, and got a few safety concerns. It's potentially lifting a lot of weight, so a lot of danger here. So I think the biggest concern is if one of the ropes snaps, it'll basically be like a whip, causing serious injury depending on how much tension is on it. I think the key thing is to know where it would go if it snaps. Generally going to want to avoid being in here. I call this the kill zone. Other potentials is the crane itself failing. I did make a little bit of a mistake. Thought this could only lift 350 pounds on initial research, and it's turning out it's a lot more than that. So before we even put the pulleys on to multiply it even further, this thing can lift probably a ton easily, a literal ton easily. Unfortunately, we don't really have a way to test that at this point. Potentially could lift a car, but I'm not sure I'm willing to put one on the line yet. So that might have to be an upcoming video where we actually get a donor car to lift and potentially drop from some height. Let's test out, see what we can lift. If you calculate all the ideal force multiplication of all the simple machine elements, we can figure out the theoretical lift capacity of the crane. The treadwheel comes in with an axle radius around 2.5 inches and the interior wheel radius of 58 inches, yielding a force multiplication of around 23.3. The tripostylus crane uses 3 pulleys, which ideally works to multiply the force by an additional factor of 3. This means we are dealing with a theoretical force multiplication of almost 70, which means a 200-pound person could potentially lift up to 14,000 pounds, which could then even be further maximized with 2 people to lift up to 14 tons. This of course is all theoretical. Friction and other elements will lower this amount, plus there are numerous other elements that could potentially fail before reaching our max yield. So let's test it out and see just how high we can go. First up, let's test the actual strength of the rope we spent a while making ourselves. "70 pounds of that rock. Leave no stone unturned." $130.
We else found yet?
Not quite. All right, 150. We are just leaving the ground. We're almost there. Oh! That is less, I think we were just shy of 200. That is, it's a little disappointing. Despite all of our hard work, our rope failed a lot sooner than we expected. Not entirely sure why. My suspicion is we didn't have quite enough twist to hold everything together into one super strong rope. And where it was knotted at one end that it broke at, it was able to break strands individually instead of the rope resisting as one solid piece. Fortunately, we have some stronger store-bought rope we can resume our trials with, but first, let's get the pulley system attached.
Here. Okay, 16 pounds.
I'm out of the kill zone for now. We're at 40. 100. 100. 140. 200. 200. Yeah.
The whole thing's tipping down.
15. Back down to 210. Back to 200. Whole thing's.
Oop.
I can keep cranking.
Oh, we're, stop. Stakes are coming out.
Oh man.
I hope the frozen ground would help our stakes stay anchored, but the day actually warmed up as we continued, turning the ground into soft mud that we couldn't anchor well into. So we switched to anchoring to the massive treadwheel itself and some nearby trees.
Yeah, I got it.
We are fully off the ground.
222. We're all the way off the ground now.
We're at 222. All right, how much heavier dare we get?
That didn't fail spectacularly.
We are partially off the ground. What's the reading at?
273.
73. So we're pretty close to off the ground. Just proceed very slowly.
Whoa.
What? Oh wow. Okay, we are lifting up.
Hold Elliot. Okay.
As we started to max out the crane, reaching around 500 pounds, the entire treadwheel started to lift and tilt forward. Without enough weight and anchors, we had basically built a giant teeter-totter. With the state of the muddy ground, fixing this was going to require probably a much larger redesign. With this first test, we already way exceeded our expectation. Trying to do this safely was definitely nerve-wracking. So going any further is going to require a new location with better anchors. Not to mention something heavier to attempt to lift. If you happen to have a spare car or elephant for us to try and lift, let me know. Pretty amazing how much we can lift with just the power of simple machines and a single human. I'm definitely going to be looking to push the limits of this design in the future. Thank you to everybody for watching. Thank you to all my Patreons. Without you, this wouldn't be possible. For now, I must go. My people need me. Flying. It's just like Superman. I've spent over a year now working on this project in the background, trying to achieve a rather absurd goal. But why? Well, because I fear for our future, and I wanted a way to cook a chicken. There's a lot of concern right now about the rise of AI and what that means for workers in new fields it is poised to threaten. Every time a new form of automation comes for a new area of jobs, comparisons are frequently made to similar events in the past, most notably the Luddites, a movement of the early 1800s. They rose up against the early mechanization of textile production, which they believed threatened their livelihood and standards of living, whose name is now synonymous with backwards facing and resisting progress. In a larger historical context, this is generally true, and people moved on to new jobs and careers. But in this video, I wanted to look at another sect of population that was impacted by automation, who never truly recovered. And of course, I'm talking about the working dog. The dog was first domesticated at least 30,000 years ago when early humans persuaded them with lucrative job contracts. In the years that followed, canines enjoyed a wide berth of employment opportunities, from security services, pest control technicians, hunting guides, courier services, ranch assistants, and as the focus of this video, the unique profession of the turnspit dog. Generally, humans have been able to move on to new jobs as automation removes previous ones, but that's not the case with dogs. Throughout history, as automation increases, dog unemployment rates have gotten higher and higher. Most dogs today are unemployed and face zero opportunities for ever getting a job, leaving them with nothing to do but lay around and are often forced to even beg for their food. And believe it or not, there's not even any unemployment benefits for dogs. So in light of this new wave of automation, potentially giving many of us a similar fate, I thought I would do my part to fight back and see if we could bring back at least some jobs for dogs. So I'm going to attempt to bring back the professional turnspit dog and get these poor creatures back on their feet with steady employment, and have them cook me a chicken. The turnspit dog is a specific breed of dog that was bred in the 16th to 19th century for one single purpose: to rotate a spit of meat over a fire in the kitchen.
What is my purpose?
You pass butter.
Oh my god.
They would continuously run in a small wheel, which would rotate the meat consistently as it slowly cooked. However, as most things seem to go, more modern machines eventually replaced this profession, and the entire breed of the turnspit dog has gone extinct. So if I want to bring back this profession, I'm going to need to first build them a wheel. So I actually started this project over a year ago and had this plan of building progressively larger projects in succession to explore ancient forms of animal and natural power and kind of figure out things as I scale up. Starting first with the small dog wheel that could be repurposed as a small water wheel, then I'd build a larger water wheel and eventually scale the dog wheel up to a human-sized wheel. Needless to say, while I did start this project first, I've now completed all of those other projects before this video could be finished. All right, so the first step, and basically the main part of making this actual wheel, basically gonna be two circles, which you then connect together, put some kind of platforms on there to walk on. So the biggest challenge is gonna be making basically straight wood into a circle. So I decided to go with a 10-sided
decagon.
So I ended up deciding to go with a 10-sided.
Decagon.
So I went through and did a bunch of meticulous cutting and sawing and chiseling to make 20 of these identical little shapes here. And my hope is they're gonna overlap a little bit and fit together. Should hopefully offer a decent amount of strength, and hopefully all my math and angles and everything are correct and this will work out. So I think I'm gonna glue everything together first with some hide glue and then finish drilling the holes. Then everything should fit together a little bit better. All right, so we got the two wheels all glued up and held together. They're solid pieces now. They were solid pieces, but obviously not very strong, as I very clearly just demonstrated. Not much holding them together. I'm going to add a little bit more strength by drilling out pegs between each one, and this will kind of help prevent any shifting, and probably add some additional glue onto everything, especially the parts that just broke. Hoping to give some nice long pegs to give the strength to the full thing, and then they'll run through into these boards, which will then connect the two wheels. We'll have a pretty decent cylinder then. Okay, I think I broke pretty much every bond that I previously glued. I left them a little too long, and driving them all the way through was a little bit too difficult. But I think we basically have the rough structure here. I just got to add the other wheel, probably tap everything a little tight again, let the glue hold, and hopefully we'll have a solid wheel. Got it together. The holes did not align perfectly, which is not great. Tried to be very careful on my math and use a good template, but there's enough variance and some primitive tools, so they're not the easiest to use. So we have a wheel-like object. That's the biggest and most challenging part of this build. I debated a lot of different ways to do this without using any nails and just all wood. And this seemed like the best strategy for something strong with just a few pins, but I feel like there's definitely things I could have done better. Woodworking without nails is not something I have a ton of experience with, and hopefully it's strong enough to support a dog. It is feeling pretty solid. Glue hasn't even dried yet. So yeah, I'll let this dry up and then start moving on to the next step, which will be putting some platforms in here and the base it'll spin on. So I got pretty much the whole wheel constructed now. Did make me realize some safety concerns. I'm sure as you breed a specific dog, they're comfortable with the wheel and they're not gonna freak out and jump out. But since I'm still training them in, I'm a little worried they might try and stick their body through one of these holes here, and so don't want to do that. Make sure this is as comfortable as possible for our four-legged helper. Also a little worried the wood is kind of smooth, a little hard to grip, there's some gaps. I'm gonna make a few modern adjustments to this to make it a little safer. So we got some artificial grass to put on top of the wood on the inside to line it, and that'll give a nice soft surface to walk or trot along. And then I bought some plexiglass panels here. You're gonna cut them and fit them, cover all of the holes. So once our little four-legged friend is inside there, they will be both trapped and cozy. Then just a process of trying to figure out how to train them to walk and spin the whole thing. Looking at other drawings, I think theirs are a little bit lighter duty. Might be a little bit of an issue because I've been trying to build this in a way that doubles as a water wheel in the future. So this might take a little bit of force to get to actually spin. With the wheel now constructed, on to the next problem, finding a dog. Now, I know what you're thinking. Andy, you famously have a cat. You've been watching for a friend for the past 78 months. You know, at this point, this might be my cat. So why not just use her? And I think that comes down to the nature of the relationship to these animals. Dogs were domesticated and employed by humans for thousands of years. Cats, however, were the independent entrepreneurs of the world. As humanity developed agriculture and started storing large amounts of grains, cats saw the free market demand for a pest control service and swooped right in there to open up shop. Since then, they domesticated themselves to get along with their new roommates, humans. Ultimately, this ancient contract between cats and humans is still honored today, as my roommate continues to protect my grain supply. But doing an actual job, like powering a wheel, not a part of that original deal. So I'm gonna have to find a dog. Fortunately, there's a dog park near me, and if you're quick enough, you can just snag one for free. I started by first getting her acquainted with the wheel and comfortable with it. That's scary. She's in! I'll take him out. So I got Holly here. She's been doing this for a few days now and she's getting kind of comfortable with it. Once I got her spinning a little bit, she did okay, but she's a little uncomfortable now, I think. So just the whole uncertainty of it moving and the floor suddenly becoming the ceiling, it's a little scary. So she's been running away whenever we try to train some more. So got this Velcroed the opening here. So you can easily kind of access it. So I can put her in there, let her get used to it again, and then slowly start spinning it and just kind of bribe her with a lot of treats, and hopefully you can get her a little bit more comfortable. Then after that, it'll be a process of, once she's comfortable with that, getting her to actually spin it herself. She's ready to go. You ready? Ready. Is that is it? You don't know. Good job. Not quite working as well as I'd hoped. She's not quite like naturally flowing with it and just going into a trot. She's kind of resisting it and just sideways walking. She can definitely make it move on her own. I don't think she understands how to intentionally do it though. After multiple attempts, things didn't seem to be working. I think being locked into a small space was freaking her out and preventing her from getting used to the actual wheel and moving it on her own, as she seemed to just focus on trying to find a way to escape. Good job, Holly. So as the next step, I bought a cheap cat wheel that was all open and didn't have to be closed off. I figured I could get her used to the operation of this wheel and then switch her back to the one that I made. Walking. Training on this new wheel had some initial promise and got her to start rotating it herself. But getting her to keep doing it continuously proved to be a bit too much of a challenge. After she had her fill of treats, she just became disinterested in going much further.
Keep running, keep going, come on, keep going. All right, run, Holly, run, keep running, keep running, keep running, keep running, keep running, keep going, a little bit longer.
In the end, I was left with the conclusion that this dog might not be the best match. A larger one that's more energetic, that's more food motivated, might be a better match. So let's go back to the dog park and see if I can snake something a little bit bigger.
Good, Rex, good job.
A larger dog requires a larger wheel, so I quickly put together a brand new wheel. I made it kind of a hybrid between the previous one I made and the cat wheel that I bought. This time allowing one side to be completely open so that the dog doesn't feel trapped. This ended up requiring some modern equipment and hardware to make it roll smoothly though. After several training sessions, things started to look very promising. Rex picked up the new assignment pretty quick and was much more motivated to keep going. After several sessions, I finally started to get him to keep moving continuously. So I thought it was time to put this apparatus to the test with an actual chicken and see if we can start cooking. So first up, let's forge the actual rotisserie that will connect to the dog wheel. So training's been going so-so, I would say. Some days are really good. He seems to get the hang of it, seems to want to know he's supposed to keep running. Other times he just doesn't want to do it and he just wants the treats. And I think you want a dog that's kind of dumb. Rex here isn't necessarily the smartest dog, but he is smart enough to know that like if he's in the wheel, he's not really going anywhere. So he's only gonna do it if he is getting a treat. I did not expect is that this dog is scared of fire. He did really good before I lit the fire. Now that I got the fire going there, he is terrified to be anywhere near it and does not want to run the wheel. So we're gonna go for one more try with another chicken on there. Hopefully that's some improvements. We added a pulley system to the rotisserie, put the fire a little bit further from dogs, and we'll also have a smaller fire that they're hopefully less afraid of. I also have both of the dogs with me today, so we can double dog this wheel. Surprisingly, they like to run on it together, which does not seem comfortable, but my hope is at least one of them will be food motivated enough to maintain it and I can just kind of keep feeding them. Ideally, you want the dog to do this on its own, but that doesn't seem to be working out. So I think I just gotta be constantly feeding them food. And go get a fire started, load up our chicken, and get going.
Girl, keep going, keep going, keep going. That's a good scan.
After about half an hour of trying to get the dogs to run in it and having mixed results, we have a cooked chicken. Even with the fire very low, can't feel any heat or smoke this time. Rex was still too terrified of the just concept of a fire being that close to him. Holly, however, was a real trooper. The only problem is I made the wheel for Rex, so it's a little bit too heavy for her. I technically did all the work and had to manually hold the treat in front of the dogs, but in the end, I think I can say I didn't actually cook this chicken. She did. But she wants my chicken. Yeah, you cooked that. Let's give it a taste, see if we cooked it well. See how good of a cook these dogs actually are. A pretty good chicken. I barely had to do anything to cook it. Yeah, it's a good girl. Yeah, you earned this. It's the fruits of your own labor. Good job, Hall. So this was not quite the slam dunk of the results I was hoping for, but after years of training multiple dogs, I think I'm gonna have to call it close enough to success. These dogs are literal pockets of infinite energy that I hoped I could harness and who knows, possibly solve the energy crisis. Only small goals here. Instead, it ended up taking a large amount of time and rebuilds and so many treats. Just trying to motivate these dogs to even move the wheel, I think they've gained a lot of weight. It is unfortunate that the turn spit dog went extinct. It certainly feels like some dogs are just born to run on wheels and do it instinctively, but none of the countless dogs that I tried with had any trace of that still in them. So I think I'm just gonna take the lazy view of a lot of employers today and just declare, nobody wants to work these days. Clearly the problem is the workforce and not my methods or incentives. Dogs today are just entitled and lazy and lack the work ethics of past generations of dogs. The world is doomed. But in truth, I found it just a lot easier to buy a dog costume and pay my assistant Theo to run the wheel himself instead. The hours of training, building wheels, and dog treats added up to a lot more than what I could just pay him. And Theo loved it. So I don't think I quite unlocked this source of free energy. I think we can take this as a precautionary tale for our potential future. The more jobs we give away to automation, the more our future might turn into the lives of dogs today, where we give up working long days of employment with backbreaking work and find ourselves transformed into unemployed, living leisureful lives full of safety, love, and belonging. That is a dystopia that might be waiting for us. And who would want that? Thank you again to all of my supporters on Patreon. Thanks for watching. One of the most powerful, simple machines is the screw, but it's also the most time-consuming and difficult to produce. Fortunately, legendary inventor Leonardo da Vinci had some ideas to speed up the process. The machine he designed was groundbreaking, but he may have never actually made it in real life. So let's put his design to the test and see if his invention will actually revolutionize our machine building abilities. Of the classic 6 simple machines, the screw was the last one that was invented and is probably the most difficult to make. I previously unlocked this technology when I made a screw press to press olive oil for making soap. Basically, I had to do it the traditional way of hand carving a screw. It was very difficult, very time consuming, and not the most effective. I think one of the biggest issues that this channel faces is the difficulty of achieving precision when you're just using hand tools that you made from scratch. So in this video, the goal is to produce this machine that DaVinci envisioned that should hopefully improve and make a much more precise screw. Traditionally, screws from the very beginning were either hand carved or filed into metal ones. To make a basic fastening screw for a long period of time, you would just forge an actual screw and then file the actual spiral into it in a very time-consuming process. I let Theo do this, and it took him pretty much an entire day to make just one screw. With a little bit of experience, you could probably cut those numbers down, but it's still not very efficient, very time-consuming, not fun. Today, the threads on a screw can be pretty easily carved in using a modern lathe, which uses a lead screw as kind of a template to carve it in a consistent manner. But that technology, and basically the great-grandfather, is what we're building today with DaVinci's device. But that technology to carve an actual thread into a screw is relatively modern in all of history. So it's not surprising that Leonardo da Vinci, who devised a lot of machines that required screws, tried to come up with a better method for making them. And the machine that he came up with is potentially the great-grandfather of the modern method of making threaded screws. Unfortunately, like even a modern lathe, making screws requires some form of reference screw. Perhaps even worse, DaVinci's design actually requires two identical reference screws. Previously, I just measured consistent marks on a stick and connected them into a spiral. This result ended up being a little less than ideal though. So we experimented with a few methods of making a consistent mark.
And the challenge so far has been how to evenly cut threads on a rod. I think ultimately we are going to have to just grind them down by hand, but getting them evenly spaced has been the real trick. So we started with a kind of tool like this that we just kind of whipped together really quick with just a sharp blade, inserted into a block of wood at an angle, and then a hole drilled through the block to accommodate the rod. Initially, we ended up with an angle like this, which I think will work, but I think we can also go a little more aggressive. So ultimately with this tool, we ended up with threading like this. And the way it works is basically you just fit it onto the end of the rod and just start turning. And the blade will cut a groove. Basically all we're doing is marking the thread at this point. And then we'll go back through and just hand file all the threads. But this is how the tool works. So you just keep twisting and cutting. It's worth noting too that because of our gearing system, these three gears are basically going to drive these in reverse. And so these rods are ultimately going to have to be reverse threaded so that it cuts the central rod in the right direction. So you just get nice, evenly spaced threads.
Then it was just a matter of manually carving out these threads with saws, chisels, and files. With the reference lead screws, now we just need to add some gears and we can start assembling our device.
Basically, we're going to work with a 3-gear system here. So we have a larger central gear and then 2 outer gears. These are going to act as the driver for the guide rails.
For the nuts that will follow the reference screws, we went for a simple solution of wrapping some of the wire we made around the threads and then glued it into 2 halves of the wooden nut to act as the threading.
So this is what we have assembled so far. This is our screw making machine, minus the cutting tool. Currently, we just have a pencil hooked up to it so we can kind of gauge the thread. Essentially, we have just like a basic frame, and then we have the cutting tool and sort of like guide block, I guess you can call it, on this end. We have 2 threaded rods, and then the rod that is set up to be cut in the middle here, which is free sliding inside the jig here. And then on the opposite side, we've got a basic 3-gear system. It looks like we kind of lucked out with the gear ratios in a way that, as you can see here, it'll be cutting threads at about, I don't know, 1/2 inch, maybe a little over 1/2 inch. As you advance the gear system, it'll pull the block forward. And as you can see, it'll run along the center thread, which spins at its own rate, not necessarily matched with this, just based on whatever gear ratio we have. And it'll ride along the rod. and slowly but surely cut into it. We've got 2 pegs in the back here. You can pull these out. They're just pressure fit, and then you can lift the whole thing up and pull the whole thing back, which allows you to replace the rods with any size thread you want and the gears with any size gears you want. So once you're done producing a rod, we just have our pliers here, simple pin holding everything in place, and then you can pop this out and potentially replace it with any other size dowel you want, because the block itself is also interchangeable. I think we've got it going. The only thing we have left is basically to put in a center hole here and then put in a cutting tool. So as far as the cutting tool itself, we did come up with several different iterations and designs. Ultimately, we came up with something like this. All we ended up doing is cutting a few small teeth in here, thanks to Theo. And it did occur to us sort of after the fact that with this cutting tool, we can come up with different versions of different widths and cut different widths of threading.
After a bit of experimentation with the cutting device, we eventually settled on a saw blade held down with tension from a spring of some of our wire. Interestingly, coiled springs were a much later invention, supposedly not being invented until almost 300 years after DaVinci. With the adjustable tension, it's now just a process of running the machine back and forth. Each time the blade bit cuts a little bit deeper and deeper into the channel, following the exact same path every time. But this is only half the challenge. We still need to find a way to make the receiving nut for our bolt. Our wire method worked for the machine, but might not provide the strongest long-term solution. Ideally, you want to be able to just carve your own threads into the wood. Today, this is done with a drill tap, a bit that gradually carves the threading into a hole. To make one of these ourselves, I found an old diagram to effectively make our bolt into a form of drill tap. But first you need a reference nut, which will keep our cutting edge aligned with the threading of our bolt. For that, we use a method that was likely used for early nuts. Pointed dowels at several points aligned to the screw thread.
There we go.
Nice.
And just attach those back together and we're good to go. And these are adjustable. I haven't glued these in yet, so we can always fidget with that, but I'd say that's functional.
Then we turn this into a jig with our target nut attached further down, with a plain hole pre-drilled into it. Then along the thread of our bolt, we placed a small cutting bit that can be slowly worked through the nut, cutting the threaded grooves into it. This cutting bit is then adjusted as we go, allowing you to carve deeper and deeper as needed. With a now functioning and highly precise bolt and nut, we can make a very useful device, such as a bench vise.
Basically, you have the nut mounted on the back of the bench here, and then you just have a couple laminated boards. You can lock everything in place.
So after a lot of hard work, mostly by Elliot, who took the lead on this project, but we now have the completed device, a screw cutting machine. I might be a little too specific to be called a lathe, but this device by Leonardo da Vinci does actually prove to work quite well. I took a bit of a challenge to actually get it up and running and carving in a nice consistent manner, but we have been able to now achieve really nice spirals. A little bit better than my first attempt by doing it by hand. A lot more precise, and probably most important is the ability to carve nuts, which actually isn't a Leonardo invention, but it actually dates back to the ancient Greeks and is a method here. It's actually very similar to how we do it today. So I think this is going to be a big game changer for helping us get to a little bit of level of higher precision. Because when you carve things by hand, it can only be so accurate. Just little variations and such can make it pretty much impossible to achieve the level of precision we're actually looking for. So screws help a ton with that. We now make a really nice vise. And we've kind of cheated a little bit by having a bench vise before this. Officially have that unlocked here with our new bench vise. We never quite got around to the process of testing if this could be actually used to cut a metal screw. There's no reason it can't though. I think it will probably require a lot more fine tuning and adjusting to actually achieve that, but the concept is all here, and probably just a process of making a file that actually work on here and then running it back and forth. It'd be really nice to find some sort of mechanism that allow it to crank all the way one way and then back in one continuous motion, so you can hook it up to an on-X source like a water wheel. So So definitely some more improvements that can be made to this, and hopefully we can upgrade this in the future for carving metal, potentially start making actual screws that are very handy for attaching things together. So historically, it's not clear if Leonardo da Vinci actually built this machine in real life. His design actually shows the threading going backwards in the middle, which might mean that he never actually tested it, but also might just be kind of a classic thing he did of leaving some errors in there so people can't copy his designs perfectly. A similar design to this, a little bit simpler, actually came out contemporarily with him that might be more accurately the actual grandfather to the screw cutting lathe today. But ultimately this is a very similar concept that happened to be invented at about the same time. So the concepts behind this machine will be very useful in our future evolutions of the lathe. So I think we're gonna try and upgrade this device in the future, but even if we don't, we're going to be applying this concept to any lathe we eventually build into the future to basically apply the exact same concept for carving a threaded screw. Probably most important about building this device is it allows us to make accurate screws and threading, which in turn allows us to make other DaVinci devices. So this is a DaVinci device that builds DaVinci devices. Thank you to all of our supporters on Patreon. Without you, this wouldn't be possible. Thanks for watching. I'm on a quest to industrialize, and that means harnessing the powers of nature and putting them to work for me. In the past, I've been able to capture the power of water to spin a water wheel and power my own sawmill. But unfortunately, I do not have a stream of water near me, so I had to create an artificial source. In this video, I'm gonna try and harness a force that's pretty much everywhere, the wind. And for my design, I'm gonna put to test an old drawing by Leonardo da Vinci and see if his unique perspective on this design actually works. So let's put it to the test and see if I can put nature to work for me. Before we begin building the full-size windmill, let's convert the sketch by DaVinci into a miniature with the help of the laser cutter OMTech sent me to try out. I've been pretty impressed with this laser cutter, so check out the discount code in the description if you want to get one yourself. So the windmill we're going to build is going to have 4 main components. The first one is going to be the actual tower that it stands on, and for that I can actually reuse the tower that I built for the sawmill. Then on top of that we're going to build the actual head of the windmill, and that needs its own little wooden frame, and that also needs to pivot with the wind so it points the right direction. Then there'll be the gearing inside of it, and that's going to help translate the horizontal rotation into a vertical rotation and also gear it up and speed it up a little bit faster speed. And then lastly, there'll be the actual sails, which will catch the wind and push it and make it rotate. So let's get started. Check out my new merchandising company, How to Make History, if you want to buy your own kit to build your own miniature DaVinci windmill. So we got the head of the windmill set up here, a nice elaborate setup to try and steam bend it, and I think I got maybe 2 degrees. So that didn't go too well, so I think we're just gonna do some slices here, so we can just kind of bend it in, give it a nice curved look. It won't be as strong, but it's not too structural for it, so we'll just do it the easy way.
This is our gearing system. We've found through previous projects that precision is key. We did have a lot of struggles with things like the rope making machine, which is why we inevitably ended up going with like a pulley type system instead of gears. It turns out the spacing between each peg is paramount to making it work successfully. If there's even like a couple millimeters off, the gearing will inevitably catch and bind up, which is problematic. However, with this, I think we've got it locked in pretty good. Also, with building a bigger machine like this, obviously there's going to be a lot of load-bearing parts, so we wanted to reinforce everything as much as we could, which is the purpose of these big reinforcing blocks on the end of each gear. We have one here, and then one in the back of this one, to the point where we even have steel pins running through this block, because we figured there's going to be a lot of torque right on this area here, and then a lot of torque on the shaft running through our lantern gear as well. In making more precise gears, we did come up with a lot of like temporary makeshift jigs to get our drill bit to go through straight. I think we're making pretty good progress. One of the concerns we have moving forward is how this entire top section will rotate on the frame. There's obviously going to be a lot of weight bearing down on the shaft and onto the frame. In some of the interpretations of the designs we've looked at so far, we're hoping have been over-engineered where they'd have like a sort of wheel type bearing system. But we're kind of hoping that we can simplify it by essentially just having a wooden nut that everything rests on. And then if we grease and lubricate the nut well enough, we're hoping the whole thing will turn freely enough in the wind. But we'll see.
The next major challenge is going to be the actual sails, which spin the windmill. And for that, DaVinci really doesn't give us much guidance. I've seen a lot of different interpretations of different ways his sails may have been intended, but his drawing is very vague. So I went back and forth between a few different designs, between things more directly inspired by DaVinci versus kind of the style used by most wooden windmills. And there's apparently a lot of different ways to potentially do this. So I ended up going with a method that I thought would be the easiest to build and hopefully use the least amount of material, which would result in something a little bit lighter and more efficient. So I went with that and kind of tried to do it in a way that gives it a decent amount of angle on the actual blades. After we actually put it together though, we found it to be pretty much ineffective in the wind without it really pushing much. It has a large amount of surface area, but isn't really wanting to spin. So I went back to do a little bit more research and get a little bit more specifics. And from what I've gathered, it's about 10 to 15% degree angle is what you want on the sails. And then actually using some trigonometry, I could figure out the angle of our sails. And then in retrospect, I realized why windmill sails are often square, even though they're coming out from a radial base, because it's easier to maintain a consistent angle. When you have them coming out at different degrees, averages out as it goes out, getting closer to the edge. By the point it reaches the end, we're only at around a 1.5 degree angle, which is a ways off from 10 to 15 degrees. And probably why it doesn't really work. So we'll have to do some adjusting. I don't know if we want to make it any shorter. I think we really want to capture as much wind as possible. So I think it's just going to be steepening the angle and hopefully getting somewhere closer to 15 degrees. So we'll give that a shot and hopefully we can get this thing spinning. Well, unfortunately, while making the adjustments, the base of the tower broke, abruptly dropping the head about an inch, which ended up being enough to snap the axle at a weak joint. So I'll have to now do some quick repairs and replacements. While I was already rebuilding it, I decided to try and improve the ability of the head to rotate with the wind by forging some simple rollers. Unfortunately, in the process of actually building it, there wasn't much wind, and there wasn't much wind for the next few days. Basically just stood still there for a while. However, winds were to pick up in the next few days, so I set up a trail camera so I could catch, hopefully as it starts to spin, and I could get at least some evidence of our windmill in action. So as the wind started to pick up, it very easily rotated the head to change direction. I think we got a lot of shifting winds because it rotated quite a bit. It's actually kind of surprising how much easier it is to rotate than actually spin the sails. So it seemed like it took a fair amount of buildup of wind before the sails actually started spinning and we got our actual motion to the windmill. You got pretty good evidence that our machine does work quite well, actually. Spins pretty good, all the gearing works, and we have a really solid base for the next steps. Unfortunately, as the winds picked up, it started to get a little bit wobbly. The rollers that I had for it kind of flattened out, making it wobbled it just enough to teeter over.
It's right, and it's racing terrible. Oh my, get out of the way, please. It's terrible. This is one of the worst catastrophes in the world. Oh, it's all the humanity.
At the end of the day, I think we can prove this design is pretty effective. We're going to take the wind and transform it into a circular motion going horizontally, and we can then transfer it to a vertical with our gearing system, which we can then eventually attach to a grindstone or whatever else we want to attach it to. So this is going to be the second part of this video. It's kind of refining this and adding that mechanism for grinding grain. In the process now, I have actually acquired a fair amount of grain, an entire field of corn that I was able to grow this last year with the intention of turning into whiskey. This is actually going to be on my new channel, which is going to be focused just on food, called Everything Foodcraft. So you have, check that out if you haven't seen that yet. I have my first video on there already. The goal is to use the corn that we harvested there and grind it using our windmill. So we have several hundred pounds of corn grain to grind up before we can actually turn it into whiskey. Should be a long challenge. So that's gonna be an actual second part video to this, is gonna be kind of refining our windmill and getting it more optimized and attaching it to an actual grindstone. And I think the big thing to optimize, and the thing that like really would be helpful if DaVinci had some creative innovations with more, would be the actual sails of the windmill. I went with a design that felt intuitive, that we should build those sails as big as possible to catch as much wind. I think I'm probably a little bit misguided with that. The more I read about it, the more I feel like you actually want them fairly small, but I'm thinking I'd probably be better off probably scaling them down. So I'm looking forward to kind of experimenting with that and refining that and seeing what ends up working best for it. Right now I feel like it's more providing too much resistance that just wants to kind of topple it over rather than spin it. So I think smaller blades. So fitting into the bigger picture, developing devices like the Windmill allows us to kind of explore capturing energy and putting it to work and the different gearing and other systems for that. But also more directly, my interest is in a device that was first invented for helping to regulate things on the windmill called a centrifugal governor. And that's a device that was first invented for windmills, but was later utilized in the steam engine, a crucial component of the steam engine. So I want to first explore its origin in the windmill. And that's kind of why we're going down this rabbit hole. Thank you again to all my supporters on Patreon. Without you, this wouldn't be possible. Thanks for watching. With that, we now have some early exploration into industrialization, while still leaving a lot of room for improvement. Each of these has been a learning experience, painting a better picture of what steps we're going to need to do next as we slowly evolve and transform these machines to be more efficient and powerful versions of themselves. Perhaps most important is going to be achieving a higher level of refinement and precision, something that's a bit difficult to do when you're just bootstrapping yourself up from nothing. So it's going to require some clever techniques, but also unlocking a more rigid material to work with than just wood, something a little bit more consistent and solid for our lathes and other machines. And for that, we're going to need cast iron. But before we continue slowly working our way to the steam engine, I did one last exploration to see if we could just jump ahead a few steps and recreate the oldest steam engine and explore if there's a way to move things along a little bit faster. It's time to industrialize. 2,000 years ago, Hero of Alexandria invented the very first steam engine, 1,700 years before the Industrial Revolution. In this video, I'm going to see what it takes to recreate this technology and see if it could be put to practical use and if the industrial age could have happened several centuries earlier. 5 years ago this month marks when I pressed the reset button on everything and started down the journey of building from the Stone Age and working my way up to my own Industrial Revolution. I started this series with a rough idea and path for getting through the Stone Age and into the Bronze Age and eventually up to the Iron Age. The steps after that for how exactly you jump the next 3,000 years of technological advancement to achieve the end goal of the series, building a steam engine and starting my own Industrial Revolution, was never really clearly planned out until now. This video is going to be both an exploration of if this entire technological progression could have been skipped, but also be the launching point for the final goal of this entire series was started for unlocking the steam engine and reaching the industrial age, laying out the effective tech tree of technologies I'll need to unlock in upcoming projects. But first, let's see if there's a shortcut from the past, the Aeolipile. It is the earliest evidence of steam being used as a power source. However, there's no evidence of it actually being used for any practical use, and is often described as a novelty or party trick. So before I start building mine, I had a quick chat with someone who's done some experimenting with the Hero's design and argues that there could have been some practical use and that it was actually pretty comparable to the early steam engines of the 1700s.
I have a Bachelor of Science degree in Chemistry and Biochemistry, a Master's in Biochemistry, and a PhD in medical research. My father was an engineering teacher at the high school I went to in a small country town, so I was in his class for 4 years. I learned how to use a lathe and all the other bits and pieces, a bit of metallurgy and things like that. So I went to university originally to do engineering, and I didn't get into engineering school, so I had to become a doctor instead. Now, at the same time, I inherited the Hero engine, which had belonged to my grandfather, and he built a Hero steam engine. And I inherited this beat-up old steam engine and thought I wouldn't be able to get it working, so I started building my own copy. And it revved up to 2,400 RPM, and my own version of it, I tried to make it better balanced and I hope it would go faster. And it went up to 5,400 RPM.
Do you know much about like the background of it, the history behind it?
Hero lived in Alexandria in southern Egypt. They call him a Greek, probably because he spoke and published in Greek, wrote a number of volumes of books about things which he appears to have been teaching, engineering related or science, and everything was all mixed up in those days. One of the many inventions that he wrote about was this Hero engine. So it started off as a drawing and description. So people knew about his work right through the last 2,000 years. years, and nobody seems to have picked up on doing anything further with it until the 1700s when the steam engine started to be developed. So this is a big burning question everybody's been asking. Why didn't they develop a steam engine 2,000 years ago? They had the concept there and didn't take it any further.
How exactly does it function? Like, how does it work?
It's actually a turbine. Well, my grandfather's one consisted of a kettle, a 3.5 litre copper kettle, sitting on a stove and producing boiling water and making steam. The steam came up two vertical pipes and in through a couple of little pivots on the side that held a sphere. Steam would go into the sphere and then come out the jets that are located on the equator of the sphere. Steam is coming out on these jets on the equator, and the two jets are pointing in opposite directions, and that creates a thrust that makes the sphere start spinning. So it's spinning on these pivots, which act as bearings. And that's a key point in terms of its efficiency and things, is how you manage to have the spin on bearings without creating a lot of friction.
So then it's kind of famously known for not having any real purpose besides basically kind of being a toy, I think. But you've done some experiments of like finding actual ways to make it do something.
All the speculation online and in history books going back, that it had so little torque that it couldn't do any work, and it was just a toy. It couldn't really be developed any further. And I felt like that's not true. It doesn't take much resistance to make it stop. It's spinning at very high speeds, 5,400 RPM I got out of it. I used worm gear to reduce the speed by 44-fold, so it reduced down to several hundred RPM instead of several thousand. By gearing it down, you should be able to get it to do some work. And my purpose in all this is try to stay as close as possible to the technology that they would have had at the time. People talk about all sorts of other alterations and things, but they're modern ideas, and I want to stick more to the original knowledge that the Greeks had and see what they might have done. And I calculated it would have an efficiency, the engine itself would have an efficiency of about 1.5% by calculating the thrust theoretically. And I made a little crane and lifted up a Coke bottle with some water in it and measured how quickly it would lift the bottle. By measuring how fast it lifted the Coke bottle, I could calculate how much energy or power it was producing. So I calculated how much energy it was taking to boil the water and make the steam, calculated the amount of power I was getting out of it by lifting the Coke bottle, and that would give me the efficiency. In practice, it turned out to be about 0.0128% efficient. And if you look at my videos, I'm getting an awful lot of steam leaking out of those pivots, and that's all wasted, lost energy that wasn't being used to drive the turbine. So that would be the place to focus on, is those pivots, as to whether they can be made to work more efficiently without leaking so much steam.
Evan uses a lathe for making his Aeolipile and has done several videos on using his more modern lathe. I'm a little bit more limited in my technologies, and while I have made several working lathes, none have been quite refined enough to work metal very well. So instead, we decided to go with a method of hammering copper into the actual hemispheres. We've previously done this with iron, and we're able to make a skillet. However, making two equal hemispheres that will connect tightly proved to be quite the challenge, and required a few attempts. Once I have all the metal in the right shape, next up I need to connect them together, and I'm gonna need a new tool for that. This guy, which is basically a copper popsicle. Before the invention of the modern electric soldering iron, this was the tool that was used. Heated in a fire or with a blowtorch, it is then held to the metal to reach the melting point of the solder. It's held to the metal to heat it up to the melting point of the solder, allowing you to join different pieces of metal together. This tool has retained some use if you ever need to solder a leaking gas line, as it allows you to solder without an open flame. Soldering is definitely a learned skill that I have pretty much no experience with. So it's a mild success with the antique tool, but before long I decided to switch to a modern torch just to help my learning curve with this skill. The main components I need to build for the device are a boiling chamber at the bottom, which is going to hold the water. Then there are pipes on either side that the steam will travel through and connect to the turbine. Then there's the turbine, a sphere with angled jets attached that the steam will escape from and propel the turbine into spinning. A very important part is the connection between the pipes and the sphere, as this will be both the nozzle the steam travels through, but also the bearing it spins around. To try and get a good inset connection, they'll limit the amount of steam that can escape, and is also perfectly round, I cast some in brass. At this point, I'm running into a few issues trying to get the Aeolipile to work. Main thing seems to be just my own inexperience with actually soldering and just the difficulty of trying to solder curved pieces of metal that are not perfectly shaped together. I feel like my skills at soldering have advanced miles, but I'm still not that great at it. I think it's pretty much watertight, but it's not airtight. So when I heat it up, some of the steam escapes out the sides, and I think that's preventing enough pressure from building up and making it into the actual spinning turbine. It also seems that like the fittings are where a lot of air is getting lost. Overall, I seem to be able to get a fair amount of steam to build up, but just not enough to actually propel the turbine. I've spent a lot of time now going back over and trying to patch things, even tried using some epoxy to fill in the gaps as much as possible. Can't seem to quite get it airtight. I think at this point I'm gonna try use some more store-bought material to see if I can get a little bit better results. So with that, I bought a copper bowl and some copper pipe that's already made, and they all fit inside each other, so I can get a little bit tighter of a seal. And this is a lot more challenging than I expected because the Aeolipile doesn't necessarily require a ton of pressure, and I think just not airtight enough to actually achieve that. So I'm gonna keep messing around with it, maybe try a few other alternatives, and hopefully finally get some sort of result. They'll start spinning on me. I spent the next several weeks tweaking, soldering, resoldering, changing the bearings, changing the size of the nozzles, trying to get this thing to work, and nothing was fixing these issues. I did manage to get just the turbine spinning though, by filling it with water, sealing it, and hanging it by a string. But then trying to attach it to something solid so that the gear could be attached was impossible. Even a small amount of friction and it would just stop spinning. After pretty much completely rebuilding a third version of it and changing basically every aspect on it, I finally started to have some success.
Let's do it! Let's do it!
So this has proven to be a lot more difficult than I expected. I think part of it is this is even less powerful than I expected, and it's super finicky. The final changes that I made that seemed to make the most difference, I switched to a copper pot for the bottom and was able to better seal that, and then I switched to a smaller ball, so hopefully a little bit less mass to try and push. I ended up switching to these 3D printer nozzles just because it's really hard to solder something that small without actually clogging it in the process. Probably the biggest thing is the actual points of contact, the bearings. That's what I didn't realize, just how underpowered this really is. So I simplified it to basically a needle on one end, and on the other end it's a small hole. In theory, hopefully the minimal amount of friction and contact. And then after that, it was very finicky trying to get just the right amount of pressure. So if you put too much pressure on it, it's too much friction for it to spin. But if you do put too little, it gets loose and too much steam escapes. I kind of accidentally got it working the first time by holding it in my hand. Could only get it on cell phone footage. Then I tried to replicate that the next day with a little bit more sturdy setup, and I spent the whole day not able to get it to work anymore. Finally got it to just the right amount of balance, and I have just basically a wood stick here just to apply just enough pressure to reduce the amount of resistance to it. It really blows my mind that someone 2,000 years ago figured out how to make this. Just trying to get everything perfectly sealed was a huge challenge, but at the very end, I'm still inclined to say that this is kind of a dead-end technology. So my original goal for this video was to try and build an Aeolipile that could actually be used for useful work. That's why I ended up going with a kind of bigger device to try and scale it up to hopefully maximize the amount of power. None of that really worked out too well. So I did put a worm gear on the spinning here thing like Evan did to try and see if I could extract some power. I found when I put my gear on it, it basically stopped. Like it was just enough resistance, even with nothing on the gear, that it made this no longer working. In the end, this was an experiment to see if the Aeolipile was a kind of a shortcut to an industrialization, and I think I have to say it's not really. The steam engines that actually came in the 1700s operate on a rather different principle, and that is going to make them a lot more powerful. And that is going to be the kind of primary goal of the rest of the channel as we kind of enter into the end game stage of the series of actually achieving a steam engine. I'm bringing back the tech tree that I had at the beginning of the series and now have it filled out to hopefully achieve the actual steam engine. And that's going to become a few different technologies that need to be unlocked. And a lot of these technologies are perhaps not directly related to the steam engine, but they are technologies that kind of improved our concepts of precision and improved our ability to make more precise devices. Because the steam engine is going to require very airtight connections and pistons and things like that. But another really important thing that needs to be kind of unlocked is an understanding of vacuum. Because that's kind of the big difference between the Aeolipile and the more modern steam engine, is that this is just based on the expansive power of steam and how when water evaporates and gets hot, it expands, and that is pushed out of little nozzles to give it thrust like a rocket. The steam engine actually uses the opposite of that, that by rapidly cooling steam, you're able to cause a vacuum. So there's a whole other side to steam technology that we have to kind of develop an understanding of. Kind of a little bit of a map now of a seemingly unrelated technologies that are gonna all come back together, finally complete the primary goal of the series, and make our steam engine. This month now marks 5 years since we first started the reset, and it has been quite a journey, and it's been very satisfying to, when I look back, see the progress we've been able to make. I just want to thank everybody who's been here for the journey. If you want to see us finish it, consider supporting us on Patreon. Thank you for watching. Thank you to all of our current supporters on Patreon. The knowledge to unlock the steam engine required viewing the world in a whole new way. If you want to expand your understanding of the world and see what it unlocks for you, consider today's sponsor, Brilliant. Ever find yourself stuck in a problem and wishing you could see it from a different angle? That's why I love Brilliant. It's not just about learning, it's about what learning unlocks. With Brilliant, you learn by doing. They've got thousands of interactive lessons that make complex topics like math, data analysis, programming, and AI click into place. What makes Brilliant truly special is how they build your understanding from the ground up. Each lesson is designed from hands-on problem solving, so you're not just memorizing, you're thinking critically and becoming a better problem solver. And the content, it's crafted by experts from MIT, Caltech, and beyond, making it 6 times more effective than just watching videos. Plus, Brilliant helps you build a powerful daily learning habit. In just minutes a day, you're learning personally and professionally, tuning your downtime into something truly meaningful. Check out Brilliant. Visit the link in the description to try out free for 30 days and get 20% off an annual premium subscription.
If you enjoyed this video, be sure to subscribe and check out other content we have covering a wide variety of topics. Also, if you've enjoyed these series, consider supporting us on Patreon. We are largely a fan-funded channel and depend on the support of our viewers in order to keep our series going. Thanks for watching.